Hello and welcome back to ST118 Statistics and Applications, Session 7. In this video, we'll explore multiple linear regression. So let me write that down. That's a big star. Multiple linear regression. Now, in the earlier video, in Session 7, we discussed the covariance and correlation, and we kind of understood that as a formula and tools for us to number crunch the data and then be able to tell us whether the data forms a line or how aligned are the data, right? I know the sentence sounds strange, but the data can be a diffused, silhouette, shadow of a line, or it is a very well-defined, you know, enumeration of the data along a particular line. And not only that, we also saw how in the video that we can use the data values to calculate the best fitting line, right? That will basically produce the least total squared errors possible. And so that everyone will get a unique line. And that's how, everyone internationally will be using throughout, right, time. So that was for the simple linear case. That means where we have one variable y and one variable x. But I was talking about those two variables more in the sense of recognizing the line. So it's like the covariance and correlation are like tools to or simplistic AI gadgets for us to say, is that a line? Is that not a line? That's all, right? So it's very simplistic and not sufficiently deep or rich enough for us to do other things. What are other things? Well, we want to certainly look at application areas, and I will begin talking about that after I list out our agenda. Then I like to look at start with a simple 2D case, right? So we call that simple linear regression, more to examine the two-dimensional data points x and y, this time not from recognizing pattern perspective, but more seriously into, I know it's a line, right? And I am going to calculate the gradient and the y-intercept, which we have done, and more, right? And we want to know a little bit more to tell us objectively, is this line meaningful? You can always draw a line. You give me 2 points, I can draw a line. You give me 5 points, I can also draw a line, but my line may not agree with your line, so we do least square. But even after doing least square, we may not understand whether this line is meaningful or not, right? But you can say, well, can't you just look at the scatter plot? Sure. Yeah, but even when we look at scatter plots, you and I may disagree, right? Especially when the data points are a bit diffused, all right? And then you say, well, this least square line, you and I will get the same line, but we will debate on whether the line sufficiently represents the cloud of data. Does it meaningfully represent the cloud of data, right? Because the data is neither very much lying on the line itself, nor very super diffuse like a cloud of smoke, right? Then in that case, what is the objective cutoff? So we need a little bit more enriched discussion, theoretical support, and calculation tools for us to be able to more objectively, you and I, right, we will do the same number crunching and agree on whether this line is meaningfully representing the data cloud of points. That's point number one. Point number two is we can see in a 2D case, right? So at least when we say, hey, yeah, the calculation does show that even visually I can agree that this least square line does seem to be a major representation of the cloud of points. But when you get into 3D, 4D, 5D, 10D, 20-dimensional space, because you have more variables involved on the right-hand side, left-hand side is still y itself, then we cannot draw a picture, right? Then we are basically a blind man trying to feel our way in this 20-dimensional space. Do we have a line? Something like that. And we will need a much more robust tool so that we can trust this tool. This tool says, reject the hypothesis that it's a line. Oh, okay, then we will follow, right? Because we can't see a shape in 20-dimensional space, right? So that's the whole idea behind this discussion, right? In 2D first, right? So we understand certain calculations, certain numbers, and then we go on to the higher dimensions, which is where this word multiple comes in, right? So multiple linear regression. And we still stress the word linear. So we're still doing linear, right? And I better talk a little bit about the word linear. Does it sound limiting, right? So we need to also do global model tests and variable significance tests. What are these? What do we use them for? Then we have need to do a little bit of the discussion of the assumptions. And then we look at a sample output. From Python's what is that? Stats models dot API dot OLS function. Okay, so that's our agenda, and let's begin by talking about the linear word. Throughout our video here, in fact, the whole session 7 videos, we are just talking about linear, right? At least for this video. Why do we use only linear? Well, later on in session 7 videos, we will try to expand this usage, right? This linearity may be constrained, right? We are limited to just talking about lines. Now, at least for now, is it meaningful to talk about lines? Do they have serious application areas and usages? Yes. All right. Short answer is yes. And we are talking about very practical situations, not a very washed down approximation or compromise in various ways, right? No, right? Because mathematically, a line is very simple. And so the mathematical calculations, the thinking, right, the assumptions that are involved can be understood much more readily by humans and mathematicians and statisticians and ourselves, right? So, but more importantly, lines, right, in practice, they perfectly straight lines may not exist unless it's very artificial, because like if you can see a line being drawn out on Mars pictures, you might wonder, right? Wow, there must be another civilization, right? Being able to draw straight lines, because we all understand that natural behaviors don't create perfectly straight lines as is drawn by a ruler like this, right? So ruler is also a human invention in that sense, right? So we don't see straight lines being drawn out in natural observations. But any curves, when you have short enough intervals, that short interval can be very nicely approximated by a line. Big curves, we cannot say that the Earth's curvature is a line. But then if you're talking, because Earth is so big, if you're talking about a small segment of the perimeter of Earth, like Singapore. Singapore is a small country, but still very large, housing about 6 million population, right? And so Singapore, this little dot, can be approximated by a line when we look at it from the context of Earth, right? So it is a straight line. You can just say, calculate the line from Jurong to Changi, one point to another, right? So you can just do that, and we don't have to worry about the curvature of the Earth affecting the line, right? So that's exactly the idea. That in many cases, we may say that the budget improves sales. Giving more budget, the sales volume or dollars will be increased as it's borne out by data, and you plot the scatter plot and all that, right? So as you increase budget, sales increases. Now, is it perfectly linear? Most likely not, right? You and I should agree that most likely not. Maybe approximately linear with some noise jumping up and down a particular line. Or it could be that it jumps around, but it starts to curve, because we also understand that when you flood the media with your product and advertisements, like McDonald's, every 10 seconds, every other minute, every other advertisement window, every other 15 minutes, you see a video, a YouTube advertisement popping up, McDonald's, da 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 da. You'll be like, I definitely won't be eating McDonald's for 7 days, right? Yeah. So it'll be like having a counter effect. So too much budget, sales starts to drop, right? But a little bit of budget, starts to rise. More budget, maybe rise a little bit, like exponentially, but maybe not exponentially in mathematical terms. It's not so explosive. We may call it parabolically, we may call it cubically, right? We will have other ways, non-linear ways to do that. Just go on to the next video. But the idea is that if we consider short enough interval, like in the small budget area, that approximation, right, the limited budget from 10,000 to 50,000, that's a small budget area. 50,000 to 250,000, right? Yeah, it's a mid-budget area. 250,000 to 1 million is the high budget area, and so on, right? So why? Because at beyond certain quantity, some other channels start to become affordable. So if you only have 50,000 at the most, maybe 20,000, your channels can only be maybe YouTube ads, right? YouTube ads, and then played less frequently, once a week, or whatever it is, right? Once a day. If you have 50 to $250,000, you might consider acting out a skit, like a purpose made, right? A skit to bring out the juiciness of McDonald's goods and all that stuff, right? So instead of just saying a static picture, urging audience to buy McDonald's, you can now have a video skit, which is of course more effective, but involves cost, right? But you also broadcast on media, social media. But when your budget goes to beyond 250,000 to 1 million, you can start thinking about sending the video to national broadcast channels, right? Which is more costly, but probably more effective for public audience, because McDonald's is a very is a product that can be made available to everyone, right? Not a targeted audience. So as you can see, linearity is not so much a constraint, right? So it is very useful, because by and large, we also have hierarchy in the companies. You're not going to be suddenly in charge of $1 million. And if you're vice president, senior VP in marketing, in charge of $1 million budgets, you also won't look at $50,000 budget, right? You'll be thinking about the big plans and all that. So that when you are looking at a small segment of a big, maybe a curved line, it is linear. And so we wonder, can we, get a good grasp of this line? Let's calculate the line equation, and that's the whole idea, right, of conducting multiple linear regression. Okay, so first thing first is our application areas. So our application areas, why do we do that, right? Application areas and usages. What do we use MLR for? We use it from the human perspective, from the business, right, life, real life perspective. MLR is just a tool for us to achieve, perhaps we can just say, uh, I can broadly say four perspectives. We want to perform investigation, right? We want to explore, so exploration. We want to decompose to find out why. So decompose is a little bit like what and why together, right? Decompose a particular phenomenon. And finally, we want to a big area of use of multiple linear regression is to use it for prediction. Now, notice that these are our functional intention. Like I'm going to investigate, I'm going to explore, I'm going to decompose, decomposition. I'm going to decompose. Not that I am going to decompose like a corpse, right? But I'm going to decompose a response, okay, into contributing factors. Now, to understand what we're talking about, first let's just look at the case of a simple linear regression, and then what is involved in multiple linear regression. Okay, so multiple linear regression, we have a lot more axes. Typically, we will have until k axis. Sorry, k is the number of variables involved. So now we are looking straight at the thing. When we keep saying multiple linear regression, what is it? This is it. This is it, right? And this is the data that we capture. This is the data we capture, right? All these. And these B's, right? The B1, B2, B3, BK, these are the coefficients we like to know. So we need them as outputs. Coefficients. We call them coefficients, right? Because they are going to be multiplied by xk. They are also the weights. They are also the gradients, right? So they are also gradients. They are also known as the weights. How heavy, is it? They are also known as the factors, right? But of course, mathematically, we will call them the coefficients. Sometimes gradients, because they are, right? So they are the gradients of the xk axis versus y, the x2 axis versus y, that's p2, right? That sense. So when we're doing investigation, we want to wait. Let me still also give a name to this. This is called the response variable. Some textbooks will call it the dependent variable, which is something I irked at. Because yes, y is going to be dependent on x1, x2 until xk, but we keep this dependence variable, this word dependence, to contrast it with independence. And independence is having a very strict definition, right? So it's just confusing to start calling this a dependent variable. Okay. Because after all, we may find that they don't work. Y is independent of x1, x2, x3, right? Then it'll be quite a strange thing to say. So the dependent variable is independent of, the explanatory variable. So that's my next next highlight here, which is the axis. They are called the explanatory explanatory variables, right? Many of them, and not surprisingly, some textbooks will call it the independent variables, which is again I am very wary of using that. So please do understand that I will keep calling the axis the explanatory variables. We are trying to explain, all right, or investigate, and you understand why from our usage perspectives, they the dependent variables and independent variables, they are very confusing, right? Because we're not so interested in whether they are statistically independent or dependent. We are interested in doing these things, right? Okay, investigation. We wonder, right? So we wonder if the response variable is influenced by what kind of factors. So that is the kind of overarching question amongst all these, right? We wonder the response variable is influenced by what factors and then to what extent. That's the so-called weight in that sense, the coefficients here, right? Um, that is the same question applied to all, although our ultimate motivation to do MLR will be pushed by investigating needs, exploratory needs, decomposing needs, right, and predicting needs, right? So here, investigation, we wonder, let's say if you're a student, then you wonder, I'm going to increase my GPA, right? So GPA is the response variable. I wonder, what are the factors? Maybe it's my habits. What are the habits that I do? Maybe I sleep long, sleep short, right? Maybe I study long, study short hours. Maybe I study with more friends or zero friend. I study alone. Right? So what are the habits or factors or practices or studying discipline that contribute to influence my GPA one way or another, right? So it could be that the number of fruit juices I drink, right? Does it help contribute to my GPA? We don't know. Okay, you have to have this humble idea first. If you know, no, that's not going to be, then why even bother to do all this? Might as well just consult your inner knowledge, right? So when we do, actually, not just MLR, but anything in statistics, we have to, at least for a moment, right? Even if you're the very know-it-all type, take the humble attitude to say, well, I don't know. Let's see what the data says. You have to do that honestly and truthfully, right? You cannot just say it because you're bluffing yourself, because you are really trying to do things that will support your own subjective judgment without proof. And we all know that, right? That's the claim in hypothesis. That's why we need to fact check, right? We need to data check. So here, same thing, right? We have to hold the same attitude. I don't know what contributes to increase my GPA or even reduce. So let me try to measure my number of hours of study, right? So in the case where you only have one variable, then we will use our best guess approach, right? To say number of hours of study or number of hours of sleep. So unless you're betting with a person about number of hours of sleep, your best guess is number of hours of study, right? So we use our contextual understanding to put in the best variable, right? The best variable in the sense that it will most likely help to explain the fluctuations on the left hand side, which is our GPA response variable. Follow? All right. So, but if you have more spaces, more spaces, why do I say if you have? Means you know how to run Python, Excel, R. You know how to drive these Ferrari engines to number crunch high dimensional data, right? To linearly regress it against the response variable. So the response variable has a very unique position, right? It only has one parking lot. It's always going to be one parking lot. I don't mean one number. In the simple case, it's one number. In the high dimensional case, it will be many numbers, k numbers, as many as here, right? Yeah. And the right side here, these x1, x2s, right? They will be numbers, but then we'll represent them as one x, as a simple x in vector form. Where is it? Right. So we'll use the vector and matrix to represent these. And we'll take a brief look at that because it will be important to understand that so that you can use them very naturally, because a matrix is like a table, carries over easily to the data frame of R, to the NumPy or data frame of Python. Right? Okay, so we were saying that the GPA is possibly, right? We don't know, possibly influenced by number of hours of study, number of hours of sleep, da 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 da. Maybe we try number of ml of fruit juices I drink per day. Okay, so we can throw in anything. We will put in everything that we think might influence or even might not, or might remotely, because at first we think it may not, like number of hours of classical music we listen to. Okay, so is it going to help? I read from some research that it does help in terms of cognitive power, but does that translate to my GPA increase? All right, that's a different story, isn't it? So I don't know. Let's put that in, right? So we don't know. We put it in, and we want to investigate which one contributes. Maybe we don't care about which one is the most important. Maybe we don't care about that, right? In certain situations. But of course, if it involves you, you want to know. You may want to rank them, sort them. Which one is the most important, second important, third important, right? Still okay. You can still do that. MLR has rich enough information for you to approximate that process. It may not, it still depends on your sample size. The larger your sample size, the better you know about reality, as is always the case. Then your ranking would be more reliable. Same thing, right? But if all we care is about which one contributes, which one doesn't, not so much about the strength, because you know that your daily lives has many things that will distract you. So even if it says very strongly here, maybe it's just by chance, right? So if you just care about which one is or is not, statistically speaking, a contributor to influence your GPA, then you can put them in. But of course, the more k variables you put in, the more measurements you have to do. So you will have to have more patience, longer time, more budget, buy some diaries and start writing down, noting down the hours you spent and all that stuff, right? Okay, that's one thing. Second thing is the gradients, the weights here, they may also be negative. So for example, the number of milliliters of fruit juices I drink, how does it affect my GPA? It could be that the more I drink, the more hyper I get, and I cannot absorb even though I'm spending hours there, right? So the more you drink, more sugar intake, right? Then you feel very hyper and you cannot focus. You just want to do exercises or whatnot, right? You're like pumped with a lot of energy that cannot immediately be used up by your brain, and you lose focus and it starts to drain on your GPA, right? So then it will be that the outcome shows BK is negative 0.5, right? So the more you drink, the worse your GPA becomes. So that will be kind of a investigation. What is an influencing factor? So that's what we are talking about. Sometimes we may also explore, right? Explore the potential reasons, potential causes. Now I need to be careful with the word cause, because time, the time variable, right, is really not a, how should I put it? Not an appreciated, not a particularly treated, specially treated VIP guest in this. If you put in time, if you put in duration is interval, so that's fine. But if you put in time, because you know that time has some orderly sequence, right? Time 10 is later than time 9 and later than time 8. So that has real life implications. But put inside here, time 10 can occur before time 5, right? Which can occur before time 1 in this universe, right? So, of course, we cannot imagine that happening, but it is disregarded. The orderliness of the timing points is being disregarded when we do number crunching here. So, in other words, the fact that maybe x2 is a timing variable. Should I study in the morning, 8 a.m., 9 a.m., 10 a.m., or study in the afternoon, 1500 hours, 1600 hours? The fact that 1600 hours is after 8 a.m. is not being exploited nor understood. It's just a number. All right. So, in other words, time loses its meaning when we do multiple linear regression. So you can put in the timing variable. Maybe you suspect, right? When you do some certain things in a day has different effects on the daily sales. Right. So should we turn on the advertisement TV facing the street, right? At 9 a.m., at 10 a.m., at 11, at 12? You don't know. You might say, well, of course, we turn it on whole day, right? Okay. But maybe there's electricity consumption or whatnot, right? So there are other considerations that then you wonder when is the best timing to turn on. So you say turn on at 9 o'clock and all that, right? But then your playing content will start to repeat, right? Or not enough, so it blacks out. So when do you start timing? Turning on the TV, the advertisement TV. I don't know, so I try 9 o'clock, then I tally with the sales, 10 o'clock, then I tally with the sales. It turns out it's not 9 o'clock, right? It could be 11 o'clock, 11 a.m., because then the office workers start to wander out a little bit and then, looking for lunch, and then they pass by your shop and they see the advertisement, they go, wow, I have to buy this. And that's why it drives up the sales. We don't know. Maybe in your town, in your city, in your the neighborhood, in your shop, the advertisement has workers that have late lunch. They only come out at 1. Maybe it's the shift workers. Oh, then you are doing the wrong thing, right? You should start advertising at maybe 12:30 or 12. Oh, these are factory environments, so they have a strict timing for lunch. Unlike, city centers where the lunchtime is a little bit more diffused. People start lunching at 11 to avoid the crowd, or they go late lunch. They start lunching at 1:30, right? So it's more diffused. But then factory environments is like ring, everybody goes for lunch. So 1 o'clock, then everybody comes out, and then 2 o'clock everybody disappears, right? Like school, and it could be also a neighborhood of schools. So when is the best time to turn on the television advertisement? You have to say I don't know. Then you tally, right? So that's why you are trying to explore what's the best timing to do that control right now. Yeah, so it's less to investigate. You know that it will affect, but I just need to know what is the selection point, right? So I'm trying to explore what's the best time in this case to do the activation, to do the action, which is to turn on the TV. It could also be recipe. If you're doing a bakery business, then you say what attracts customers. That means maybe this is the sales, right? Okay. How can I make customers like my bakery better? Right? Is it more sugar, sweeter? Is it more butter so that the fragrance is there? Is it more this? Is it more that? Is it more vitamins? That means I label, hey, this bread is enriched with B12, E, whatnot, right? So, wow, so health conscious people, when they see this, okay, it doesn't taste good, but I like the vitamins, so they buy. Who knows? I don't know, right? You have to keep that mentality, and then you can benefit. All right, so you start getting data all the time, thinking, reminding yourself, I don't know, let's try this out. Okay, so now, and then decomposition is kind of similar, you can say, but the orientation is the starting point in our business thinking or daily life thinking, slightly different, right? So we have this variable, this response variable that we are interested in, and we wonder, right, what makes it work or what makes it work harder. So it's a little bit like your GPA, right? The student's GPA. How can I improve my GPA? I'm already a good student. I have a very high GPA, right? So I want to make it more. I want to have higher, even higher GPA so that I spend 24 hours living. I might as well do the things that will heighten or bring up the probability that my GPA will be brought up further, right? So we're trying to decompose, right, the GPA into uh, various actions. So if you think about it, GPA is like a very virtual thing, right? It's just saying it's just a number, and this number is just showing good or bad, right? Or some gradation of good or bad. But my physical action, which is my study habits, my living habits, right? So it's no longer just about studying, but living habits might also contribute to increasing or decreasing the GPA. For example, going to the library casually, not for the purpose of revising for tests or exams, but just go there and read about some any book that strikes your mind, right? So going to the library, hours spent at the library, hours spent at school functions or some career networking events and all that. They don't really relate to your GPA, but you just go there, then you chance upon another event that is about, hey, someone is organizing a exam, statistics exam study group. Hey, thankfully you went for that career event, which is nothing to do with GPA, but then you chance upon something else that relates to your GPA. Right, so all these are chance encounters and a bit random processes that we can't foretell. That and we don't know. We can't do it in a very sort of analytical form, right? Like, oh yes, this is black and white. You go for career talk, you definitely will increase your GPA. We cannot say that, right? So it's a chance encounter, serendipity kind of situation. So we by decomposing it, we then say, oh wow, it does help. So I now know that I should, when time when time is available, I should try to get into some career fairs, career talks, or those seminars or whatnot. Okay, then we now know the. I hesitate to use the word reason, right? Because reason gives rise to the idea of cause and effect, and we are not really doing science here. Huh? We are not really trying to say that you do this, definitely that will happen. What the outcome here says is that if this happens, the pattern is such that that seems to always happen together when this happens. So it's just a pattern recognizer. So remember, it's still an extension of the simple linear regression to multiple cases. So it is still a pattern recognizer. When these x's, x1, x2, x3 to xk, when these x's have those values, then some product by the b1s to bk's, you will get this kind of pattern value for y. That's what it says, right? Of course, in real life, that seems to be enough. So that seems to also carry on with the implication that if you do this, that's why this will happen, right? Again, it is just a inference. That means we just seem to get that benefit as well. Although MLR is not trying to explain we are trying to do our exploration and trying to do our own explanation, but MLR itself is not trying to give the cause and effect, right? Okay. And because of that, because of the lack of cause and effect, right? Or doesn't care about cause and effect, we can actually put in the time, because cause and effect implies that something happens before, therefore something happens after, right? Cause first. Cause is always first. As I said earlier on, the time sequential timing effect, one comes before another. That kind of meaning, even if you throw in the time variable, the absolute time variable, time of day, day of year variable inside here, you will not, right, expect the MLR process to respect this orderliness of the time sequences, the numbers recorded in the time variable. It will not. It will not care. Right? It is as if time can reverse itself, time will be swapped, time will jump randomly. Doesn't matter. I just treat it as any other variable. That's it. Right. So a little bit of a caution. That's why the cause and effect is not implied in this mathematical procedure. Fortunately, most of the time it works, right? So most of the time when we say in the past, when my sleeping hours is this and this, it will lead to my GPA being this. In the past, when we have this amount of budget for advertisements and number of employees and number of hours of overtime and this and that, all the business variables, it will lead to this profitability, right? And these are all investigation, exploration, decomposition, right? Decomposing, depending on our starting point again, right? Decomposing the profitability into previous factors to make it do better. So we do better. So oftentimes it still works that things happen in the past and we number crunch and we get this behavior. Then we think that if we do more of that, right, more of overtime, more of bonus or whatnot, right, then our productivity, our profitability will increase. So the cause and effect seems like, doesn't matter, right? There's no guarantee of cause and effect here, but we seem to be able to still take advantage of that as if there were cause and effect, right? But one more surprising thing is that because of the lack of appreciation of time, time variables thrown in, I don't care, right? It's like I just number crunch, says MLR, that we can also do prediction in a very interesting way. Now, prediction, right? So let's say the Y is the stock price. Stock price, I like to know what drives it higher, what economic variables, right? Because economic variables can be observed or read about in various news outlets, right? News reports, political announcements, news, right? Government incentives, and then the kind of damaging events like earthquakes, right? Floods, tsunamis, whatnot. Okay, so what are the events that will drive up the stock price? Yeah, so we do that, right? And then we can do the decomposition. Then we use it to say that, oh, the OPEC, right? They start to increase the volume of production. And so when you put it in, the prediction is that the price will go down. Oh, okay, fine. I better sell my stocks or something like that. Oh, I better buy more stocks. Depends on what your goal. But it is then able to predict, right? This is not the interesting part. The interesting part is oftentimes we don't want to know about or predict about the stock price falling after we saw that the stock price has fallen, right? I mean, that's not prediction anymore, right? Although in this model, it is still prediction in the sense that the numbers x1, x2, x3, x1, maybe in the data it was 5, 6, 5, 7, 9. So we have never observed the value 3. So we plug in 3, what, and then the rest of the numbers, what will be the value of y. So in that sense, it is predicting because we have never seen in our data points the value 3 before, right? So when we plug in 3 plus the rest of the values, 3 we have never seen our data points, that's considered prediction because we wouldn't know what's the number, so we are predicting. But that is not the interesting part. The interesting part is actually in real life we care about what we say as the forward-looking variables. Right? Economically forward-looking variables will be those that will foretell the rise of stock prices or the fall of it, right? In terms of timing, in a more accurate way, in terms of magnitude, in a more reliable. So in two ways. So economic those economically forward-looking variables, uh, people tend to say, right, like stock market prices, they are forward-looking, because when government relaxes certain policies that will boost economic development, then stock market reacts immediately the next day, right, and or the next hour, the next minute. Well, because stock market will then price in all the future economic benefits into the higher stock price, right? Oh, which firm will benefit, so the price will shoot up immediately. So that's like forward looking, and true enough, right? So 3 months later, 6 months later, 12 months later, indeed the company is starting to announce a lot of profits, right? Something like that. So that's forward looking. And if we are trying to predict the stock price itself, remember stock price is predicting the profits of this company, maybe for this year, right? So if its stock price rises because of government announcements, then we can expect, with high probability, of course, that at the end of the year this company will profit, right? So that's like a forward-looking uh, telltale sign. But if we want to forecast or predict this forward-looking telltale sign, then we need other economic factors or observations or measurements. What are those? Isn't that a very interesting and even money making calculation? Yeah? So very, very important, right? So give an example. Suppose uh, suppose government has been increasing, right, the taxation in the past. Let's say taxation on property, right, or estate tax or whatever, right? So has been increasing taxation in the past. Then uh, 12 months later, there is a 60% chance that this company's profits, actual profits, fall. That's true in the past. Okay. Yeah. So suppose that is true in the past for this company. So now the the government has announced an increase in taxation, right? And for the third time, right? So what will happen to the company? Or what will happen to the company's stock price now? So the thing is, the announcement of the taxation seems to be ignored by the market right now. But then you did this forward-looking job, right? So you say that, or your model tells you that this forward-looking job, uh, the government taxes increases tax now. 12 months later, the company will start to announce a fall in profit, right? So 12 months later, the stock price should fall. And then if your model is good enough, it will even tell you by how much. Like 60% chance that it will fall by 5%, something. Oh, that's powerful, right? Yeah. So the idea is to shift the timing of the variables. So shift the timing of the variables. You align the 3 year, uh, 3 years ago action to current stock price, something like that. So you can kind of misalign the variables. So the stock price now can be aligned with the amount of tax the government imposes 3 years ago. So you shift the columns. Right? So 3 years ago, so 3 year government, 3 years ago government taxation aligns with today or this year's company's profit. Right. So and then this current day's company stock price or something like that. The idea is to shift the timing of the measurements. All measurements will have some timing, right? Because we will always measure things sequentially. But you actively, you knowingly shift the variables timings to not misalign, but purposely try out. Let me try 3 years. Let me try 2 years. Let me try 1 year, right? Similarly, the stock price. How long later will the company suffer a fall in stock price? Let me try 6 months. Let me try 1 month, 2 months, 3 months, 4 months, 6 months, 12 months, 13 months, and keep going. One of those will be having a very strong significance. So maybe that's the one. Right? So these are all data analytics. They go by shifting the timings, various combinations of shifts. Of course, super intensive because you are running the same model but shifting the data columns here to align the timings differently in order to achieve some sort of a model that best gives you the forward-looking prediction ability, right? That kind of approach will be very intensive because you are creating perhaps hundreds of thousands of models, right? In order to find so-called the best model, you're using the same data, but the data is being shifted, right? And differently aligned. I don't want to say misaligned because you knowingly, intentionally do that, right? So we are differently aligned, and then you create a model. You align them slightly differently again, you create another model. And if you have 10 different variables, then you have a combination of, you know, shifts, right? So you can you will have to shift them in various combinations. You try to find the model that has the strongest significance, what we say. Then you say that model should be the forward-looking model. That will help you predict very powerful, right? But of course, whether this shifted model makes any sense is another business. But again, it allows us to do prediction in a forward-looking sense based on past, right? So many applications if you think about it. And of course, if you have a powerful computer to search for the best model based on same data, but variously combine them, variously include and don't include some more. Because some variables, when you include, they would make the entire model lose its shine. That means the more variables you include, the worse it becomes. The less useful the model becomes. Then you question. So which one is the best set or subset of variables to include? Oh, that's called a stepwise forward refinement, right? You can add variables one at a time. Of course, there are various combinations, right? And you can also do a backward filtering. That means you first include everything. Maybe that's the best. Then you remove one, see if it's better. Then you remove another. Then you try to remove both, right? And then both means k choose two, right? So you remove two variables systematically, not randomly. So try this two, try the other two, try the other two. So you keep doing that, you will generate many models, right? Based on the same data. Which one is the best? So again, that is very intensive in terms of computation. And but hey, right, these days we're talking about data analytics. So you want to choose the best model in order to be able to give you the best prediction, which could be $1 million business. Yeah, so it is worth the while. Okay. So I hope I have enticed you, right? Make you start drooling. Oh wow, so I can really use this a lot, and in the most parts, it's quite true that if you can do this, uh, already it allows us to do a lot of things. This alone, prediction alone, right, allows us to know the situation beforehand. And if your model is accurate, predicting things very reliably accurately, yeah, then you win because you will always be buying low, selling high, right? You'll always be making the right decisions, at least 90% of the time, right? Even if you're making the right decision 60% of the time, that's already very powerful, right? Much better than just guessing in very complex situations. Okay, so I hope you can uh, widen this even further, right? Starting from these humanly induced goals and intention for applications. So next, we like to motivate the understanding of multiple linear regression using 2D simple linear regression example and a diagram. So first thing first, let me re-emphasize that this is SLR, a simple linear regression case, and this is MLR. The difference is only in terms of the number of variables, right, on the right side. As far as the terminology is concerned, one variable case, simple linear regression. But of course, any theory that works for MLR should also work when k equals to 1. Yeah, there should be nothing special. Although, of course, when there is only one explanatory variable, things may simplify, things may short circuit to give very trivial, or equivalent implications when we have other tools and information about various aspects of the variables. All right, and now all the variables disappear. There's only one, so we might have all the reports having the same information. And we'll have a look at that later on when we look at the sample output. Okay, so the idea of 2D, most important part of this 2D discussion is, I would say, the diagram. Okay, because I can only draw a diagram in the 2D sense, x and y. I may try, all right, but I will struggle to draw a diagram in 3D, okay, with the data points floating in the cloud, but then flattened to my piece of paper here. And that is not very helpful because you probably also wouldn't get to experience the 3D effect unless I rotate it, right? So what I'm going to do is do a quick snapshot of what we have seen earlier on in the previous video, right? That this is the X bar. I should have done the other way around. Put in the data points first, but and then calculate the X bar and Y bar. But this being a constructed illustration, I'm just trying to illustrate, right? So point number 1, point number 2, point number 3, point number 4, point number 5. Okay, there seems to be some sort of a line right now, yeah? So that's the thing. And we will perform linear regression, right? So that we will get the least square line. And I would want to just put it this way. Okay, so this is the least square line. And we discussed what is least square, right, in the previous video, so I won't do it here. But I still need to show the kind of like a vertical difference of the areas, right? What I want to show is the sense of SS model. Okay, the sense of SS model. The sense of SS model is the sense of these points, right? So if I put a little cross here, these are the what we call the predicted points by the line. In other words, they have the same x value, but different yi values. We call them the y hat, the yi hat. So the data points are what would be meaningfully the fact, right? So we'll treat them as kind of like sacred. They are factual. So this is like y1, right? So this is the y1. y1 is directly measured off the y-axis. Huh? So y1 is 5, means from 0, 1, 2, 3, 4, 5. It is 5 units tall. y2, and so on. But this one, in contrast, would be like 4.3, right? 4.22 or whatever, less than 5. And this is what we call the y1 hat, which is the predicted value if we plug in the x1 into the model. What is the model? The model is given by y hat equals to b0 plus b1x or xi. So yi, xi. So just attach the suffix as necessary, where b1 is given by ssxy over ssx. Yeah, ssx is the sum of squared deviations of each point from the x bar. These are the summing up these squares. I won't draw them because that's not what I want to show here. Right, and then the and ssxy will be the sum of products. I guess you don't call it square, but sum of products of each point's x minus x bar times y1 minus y bar. x2 minus x bar times x2 y2 minus y bar. Right. So that's a xxxy. You add up all the areas of the rectangles. Then b0 will be just using the y bar minus the gradient times x bar. So we can get the y-intercept because we plug in the x bar and the y bar, and we should obtain the b0, right? So this is b0. And of course, from the equation, we should see that x bar, y bar should pass through. So so this point should be on the line itself. Okay, the middle point is on the line itself. A little bit of a misalignment in my drawing. The implication is that x bar, y bar should pass through the predicted line always, right? Always. Okay, but from here, we can see then that we have this idea of the SS total, SS model, and SS residual, right? So that is, again, a very important part of our understanding from this 2D example. So the idea is that we want to say SS total is the total fluctuation of the response variable. So SS total, right, is equal to the total fluctuations of the response variable. Variations being a more official term of response variable. And that's given by summation of all the i's from 1 to n, y1, yi minus y bar squared, right? So the squared deviation of each y from y bar. So we take the y bar as standard and the vertical difference, right? And then squaring it. So we take the vertical difference from the data point, the data point itself, and squaring it. So the data point itself and squaring it, the data point itself to the midpoint and squaring it. This is a very tiny one. The data point itself and squaring it, very big one. So this is the sense of total fluctuations. If we add up all these areas, right? This is different from our SSXX, SSYY. SSXX is, oh, actually, this is also SSYY, right? So SSXX is this point's x-axis from the x bar, and then this will be a very huge area, right? So that's a different number. But indeed, this is SSYY. Now, SSYY, y plays a very asymmetrical role because you see that our mathematical procedures and calculations and even actual application worries is all about the response variable. The response variable, right, is what we are trying to investigate, explore, right, potential influence and factors, decompose it into a finite number of factors, right, and the weightage we care about which one is the strongest, weakest, and then we may want to use that model to predict, right? So Y has a very privileged position or very special position or even a patient's position. We want to do a surgery on it, right? In practice, the Y is a special position because it is often very important to us. Okay, so it is very important to us. It is very often hard to measure. It is often expensive to obtain and sometimes impossible or very rare to obtain. Impossible to measure. Okay. Explanatory variables, on the other hand, they tend to be uh, they are easier to get, right? So they are easier to get, easier to measure, ready to measure, occurring in abundance. You don't have to wait for a long time for it to happen. Expensive, and in this case, cheap, relatively speaking, right? So cheap, expensive can be why takes a very expensive equipment that is worth $3 million to buy. After that, you can take all you want, but then buying that equipment needs $3 million, right? Whereas, relatively speaking, the X variables would be cheaper to obtain. So, for example, a electronic uh, measuring device, right? A very huge medical device that is safe, for example, measuring ECG, EEG on the heart, right? The heart with very nice outputs and graphs and USB export or of the data and whatnot for analysis versus a stethoscope where we do human counting 1, 2, 3, and then, within a minute. Then we use that to estimate beats per minute. Any irregularity, we go by hearing, right? So everything is more manual but less reliable, right? So it's cheaper. Stethoscope is a um, cheap medical instrument. EEG, ECG measuring machines, oh, right, more expensive, right? A lot more expensive. So cheaper, right? Easier to obtain, and at least possible. Maybe widely available, not just possible, but widely available or readily available. All right. So if both are rare, then at least it is readily available. You don't have to prepare the scene and do some things and to in order to capture the scenario or the measurement. Right. So that's why when we have a model like that, the right hand side is under control. So we control the experimental control. For example, we were saying the GPA, right? GPA is something you want as high as possible, but you cannot set it to a number like 5/5, right? But you can control your number of hours of sleep, number of hours of study, number of milliliter of juice to drink, number of hours of classical music, right? You can control. This one, usually out of control, no control. No control because it's other people's stuff. Other people can control. You cannot control. So relative to you, it's like no control. Or absolutely no one can control. For example, um, rainfall, right? Milliliters of rainfall, and in areas of perennial flooding, that's a very even life-saving model if you can predict accurately, right? So you have no control over the milliliters of rainfall, but if we know, if we observe, right, we can't control temperature also, for example. Daily temperature we might not be able to control, but they are forward looking, right? They are past occurrences to predict the future. So we either we control, in that sense, we know the past history, right? Then we can predict the uncontrollable, future, unmeasurable, impossible to measure milliliters of rainfall, right? So if in the past there have been at least 7 days of consecutive high humidity and at least 5 days of high temperature, like above 7 degrees Celsius. You know what? Yeah? So you just fix all these parameters with the help by geologists and weather experts and physicists and various, to build the models. And this is what we're talking about, building this model, right? So that the right variables are involved, the useless variables that pull people down, right? The moment you add in, you cause problems. We take them out. One quick example: number of hours of study and number of hours of sleep. If you measure over 24 hours, you find that they are strongly correlated, right? Because the more hours you study, the less hours you can sleep by definition, right? So the more you measure these two variables, the worse the model becomes, because adding in the hours of sleep kind of causes confusion to the model, right? So you may want to take out one, right? Or else you want to like measure the quality of sleep rather than the hours of sleep. Okay, so if you sleep more, but not very well, because you always wake up intermittently or whatnot, right? So you guys know that your health watch will tell you some sort of a quality of sleep. Okay, so if you measure the quality of sleep, then it's okay, right? So it's not having some conflict. So we identify all those and we strengthen the model by improving the model significance, something we will talk about in global model tests. That's why we have to test, is this model useful or more useful than if we add in another variable that likely has a problem with some existing variables, right? So it's like tearing them down. Just like how human teams tend to behave also. You may have some interaction effect. Same thing here. So we have a team of variables, but you can look at them as team of experts, right? Or team of students. And they exhibit some behavior, right? Just like students, even experts. So there's some politicking, there's some I don't see you, you don't see me well. And so the more you include, right, the more samples you include for these variables, interacting variables, the worse the model becomes. And we can see that in the uh, reports, analysis reports for the models thus formed. Right? But let me finish up the rest here. So SS total is going to be the sum of the light green squares. And this is actually what I want to talk about rather than showing how to form the least square, because we'll discuss that in the higher dimension case all at one go. Okay, so we have the SS total, then we have the SS model. The SS model is the total variations of the total variations of the prediction of predicted um, points. Of course, prediction comes from the model, right? So the model, so SS model. Which one is the model? This one. So this one is the model, right? So these models, when we plug in the X, we got a prediction. So this is the Y hat. So it should have some similar mirror image of SS total because we're ultimately going to compare them, right? So this would be our model means our y hat, yi hat minus y bar. So the reference level is still this y bar. Remember y, we're just talking about y. All these are talking about y, never the x. Because remember, the x is something we have good grasp of. Nothing to, in some sense, little to no uncertainty. We control historical, maybe we cannot control, right? Like weather temperature, humidity and whatnot. But we got those as historical data. So no uncertainty, right? So the X part is all within our controllable arena. Y is what we want to know. So we do have some historical data of Y obtained through very expensive budgets. For example, we are testing the new cancer drug efficacy. So in order to push out, we need to clear some clinical trial and we need actual maybe end stage volunteering, right, who sign consent forms and all that, patients to try out the drugs. And in that case, we need, you know, patients of that nature. And suppose this drug is only applicable for adults, then you might even have to filter out, right? You know, certain ages so that you can conduct the experiment. For example, Alzheimer's disease, Parkinson's disease. You mean that for seniors. So you cannot just take from the general population. You can only take from the the older age seniors population, and it has to have those exhibited phenomenon medically cleared everything. Then you go in, right? So it will take a lot of budget, small sample size, right? And very hard. When it is small sample size, you also have small sample size here because they have to so-called not paired but synchronized. So when you have the x1 to xk, you must have a y1 sample 1. When sample 2, you have x1 to xk, you must have a y sample 2. Right? Short of any one of them, you cannot continue that line. You have to delete the entire line. So it's kind of like a extended pairing. If you remember the PET test in two population means tests, right? So this part we don't have an equivalent from our early studies. So SSY is the overall fluctuations, right? Overall sum of squared deviations from Y bar. But we kind of appreciate this SSY in a new light. We call it the SS total. That means there are these total fluctuations that we have on hand, that we observed in Y. Can we use the model to similarly fluctuate in the same way when the X values appear as X1? I put an X1 here and not X because intention is there is also an X2, X3, X4, X5, X6. So just that I'm not drawing to confuse the diagram here. Huh? All right, so we are looking at it from a new light and say we have these total green totals, and we would like to have a model to create some squared areas, right? That would be the same as the green totals. Yeah, so that's the kind of situation we are trying to go at. Again, I'm going to try to use something light, right? So this being the predicted, so it will be here. A square because the definition is that it is squared, right? So we will use a square here. Can you see the semi-orange color square, right? So this starts from the y hat because we have a y hat minusing off the the y I hat minusing off the y bar, right? So this is the y bar. And the idea is just like taking reference from the y bar. So this part shares the same, and it has a smaller square here. In other words, smaller square is good, right? Because it is like saying I am, or rather the square that is of the same size as the green is good, right? So that it is mimicking the recreation of that fluctuation. Remember the y, the actual data points y, that means the green squares, they are natural phenomenon or they are uncontrollable phenomenon like GPA, right? So they are fluctuations. Your GPA fluctuates from semester to semester. Your exam score, assuming same difficulty, your test scores, right, fluctuate from test to test. And that fluctuation is natural phenomenon. As exam gets harder and harder, right? Exam score gets lower and lower, or higher and higher maybe. And so that is just you know native behavior between x and y. So we like to recreate that by capturing those in our line. So that's the interpretation behind that. Now our x y hat, sorry, is now very close to the y bar. This is now very close to, but now at least we can see visibly, right? And this is also having the same line, but we can see that it is able to stand on its own here. Okay, fortunately my data points are far away enough to give room to. Okay, I hope you understand by now. The orange lines always initiate from the pink model line, right? When the x's are replaced by the x1, x2, x3, x4, x5 respectively. And we have one last one, which is SS residue. I'll just put resi, right? So that's the total variations of the noise or remaining errors. Residuals. Now, in case you wonder what are residuals, it's a very beautiful term to describe errors. Okay, errors are very negative, right? So, not nice, but we will call them residual, right? So that it sounds nicer. So these are called errors, basically. Error seems that we want to discard them. We want to throw them away. They are unwanted, right? But the mathematical calculation is the same, which is that taking the data points as fact, as correct. Yeah. So yi is the data points y value. That's the fact. And our prediction is the yi hat, is what we think, right? The extent of the data point should be based on our model. So that's the error. The discrepancy squared is the square error. So that is going to be brought out. I forgot to color here. Going to be brought out by again a vertical interval and then sort of induced into a square area on the diagram. This time around, I'm going to use red, right, to highlight this. Again, this vertical interval. Can you see here the x point and the circle data point? This vertical interval is the error, but when we square it, we induce a square here. Okay, so we would like, of course, this square error to be as small as possible. That's the whole idea. Yeah, and for the square error to be as small as possible, the orange recreated variation should be as close to the, not large or not small, but as close to the original green square as much as possible, right? Then there will be no more room. So let me just try to recreate. So at this point in the residual calculation, there's no more y bar. Right? It's just between the predicted x point and the original circle point. So x point and the original circle, like here. So over here, And I try not to cross into other people's space, but looks like I have to. Okay, over here. You get the idea, right? So we keep on doing this, sometimes overlapping other people's other points, squares. Over here, right? A little bit harder to see here. That's why I want to have 5 points, so that if a particular point or points, right, is giving difficulty to illustrate, then at least other points can show similar squares, right? The whole idea is just to sum up these squares, just like the orange and the green, right? No surprise, right? Because then it's fair to compare them. Okay, so here I want to show this as the red error squares, right? So some of these squared areas induced by the discrepancy between the model predicted y values and the data points y values. Aligned at the same x, of course, right? Then it's fair to compare. Will be like this. Now, very importantly, the after everything, after all these calculations, very importantly, we need to understand that SS total, a bit like ANOVA, right? SS total is SS model plus SS residue. Okay, so this is an equation. So the total fluctuation squared, right, is always going to be decomposed into the model's fluctuation squared plus the unexplained error fluctuation squared. So this is not an approximation, but always going to be respected by SS total, SS model, SS residual for any multiple regression. So what have we got, right? The idea, of course, is to calculate the r square. We will talk about the r square. Where's our r square? Okay. So the r square will then be understood as the SS model divided by the SS total. Right? And this is the value that will always be between 0 to 1. Obviously, right? Because the SS model will never be larger than SS total. So this number, we like it to be as close to, yes, 1 as possible, because we are trying to make the model swing or create variations, therefore the orange squares, as much as possible, so that it would mimic the green squares. The green squares are the given, we cannot change them based on the observed y values. But there's ability to change the B0, B1, B2, B3, right? All these BK, the coefficients, so that when they weigh against the x1 to xk, they create a line that will, of course, when we substitute into the x values, a point such that it will be as, or create an area that is as close to the original green square as possible. But for that to happen, it also means that the recreated point, the predicted point, the x point that I drew here, they should be lying on the dot, right, on the data point. And we already know that it's impossible given that we have more points than the ability of the line to accommodate, right? Because a line can go through any 2 points, but not 5 points, right? So in higher dimensional case, same thing, right? The hyperplane can go through maybe some points, but not all points. And we want to have a lot more points. That's a whole study of statistics, right? So we will have higher sample size. So we ought to have higher sample size. And when we have a lot of sample sizes, it may be that the line doesn't go through any point because this is the least square best fit line that we have been talking about, right? So R squared is what we call the coefficient of determination, right? So what's a good name here? Coefficient of determination. Now it determines uh, the fuzziness of data. So what does it say? If it's close to 1, very, very good. The data points hug the line. They lie basically on the line because it's perfect. SS model is equal to SS total. That is the only case, right? Only case when you get 1. When you get 1, all the x's, they are on the data points. And for that to happen means the data points originally occurred already as a line. Already forms a line. We just find the line, and of course the least square line will be the line that cuts through all the points. Imagine a line that cuts through 5 points. All are collinear, right? Then it means that our model will also accomplish the same, that means the orange areas will also be the same as the green areas. And so it'll be one something over something, same thing. So cancel 1. But when that happens in real life, you want to reject because it's impossible, practically speaking, right? So we do know theoretically it's the best, but when we see this, we also get very scared. We are not going to believe it, right? We are not going to accept it. Something is wrong. Did we do the settings, calculations, measurements wrongly, right? Or if it is data submission by other people, this is cheating, right? Something is wrong. Highly suspicious. So when R square is very high, we suspect. When R square is very low, we don't suspect, but we are very disappointed, right? Because our model is a flop. It doesn't even account, let's say it's perfect 0, then it is totally not explaining all the green areas at all. It is unable to recreate the waves, so to speak. So if each square is a sort of a wave or feature created by the y, the response variable, then we want a model that will recreate that. So that when you can recreate that, that means very likely we are getting onto it. Right? I say very likely, right? It means you can, for example, you have Rolex watch, right? You can mimic Rolex watch, a particular model, and make it look so real these days. Does it imply that your manufacturing process is the same as Rolex? No, of course not, right? Yeah, so and that's what we are trying to say here, that when we can mimic the same fluctuations, then our model likely is doing something right, right? But also we have to say it with a pinch of salt, right? That okay, I think we are quite fortunate here, right? The model seems to be accounting for 0.95, right? 95% of the fluctuations can be accounted for. We never say therefore it's a good model or that's it. Although quietly we will use it that way, but you cannot officially announce it as if scientifically you have discovered some truth. Understand? So that's the qualification we need to have. We always must keep in mind we are not doing science. We're just observing that, hey, if you throw in this, you manage to recreate that. Why, we don't know. So again, for example, if we have more budget, we get more sales. More budgets and more employees, we get more sales. Why? We have no idea, right? Because it just happens that the numbers show up as that pattern, and we found a linear model that can recreate that pattern of input this number, it recreates that number mostly. So that's why this qualification is very important, because we cannot say that, high employees always will explain this, because when you use this so-called principle, as if it's scientific now, to put it across to another company, another industry, another business in another country using another culture, it may flop totally, right? It may destroy the profit. Okay, so it's just like not working. How do you call it science when it's not working, right? But why does it work in your company? Because for now, in your company setting, based on this data, in the past months, this being post COVID-19 and all having all the tariffs and everything, politics in the world, right? We observe this phenomena. So likely for our company, for the immediate next few months, maybe up to a year even, because our employees are not going to change a lot, right? There will be attrition, new hires, but it's not going to change a lot. The management is going to change a lot, and that's why the culture is going to maintain. Things will be status quo, like holding all other variables that we know and don't know constant. So that's why the model seems to continue to work, right? So we don't know. We are not going to be able to explain scientifically, like as if it's a scientific fact. Always remember that multiple regression still ends up being like a pattern recognizer, right? A plane recognizer, a plane, not the flying aeroplane, but a plane, a 2D plane, a hyperplane in higher dimensions, a line, right? A line recognizer, a linear space recognizer when I'm given higher dimensional data points. Okay, so that's it. Because 20 dimensional data points, we hardly can see a plane or Superman, right, or a line. It's very hard for us to see any shape in high dimensions. So not bad. At least we have a linear recognizer here, right? So multiple linear regression gives us that. And we need to look at this R squared to know how hugging the line or the hyperplane in high dimensional space are these data points onto the hyperplane that model that we have computed. Okay, very hugging, very close to one. Not hugging, not close, close to zero. We like it to be close to one. And also another very related uh, notion is the coefficient of adjusted determination or adjusted R squared. R squared adjusted, maybe we call it, right? And that is basically our 1 minus, yeah, uh, SS residual, receipt, divide by the remaining n minus k plus 1. Okay. And over SS total. So it's still over SS total divided by n minus 1. N minus 1, I hope you can see that this is similar to the degree of freedom we talked about in the equivariance test, equivariance F test, right? The denominator shows n minus 1. So think of this denominator like some sort of sample size. Okay, so adjusted sample size. Then it is like the average square and the average error square. So the average error square over the average green square, some sort of thinking process to get the intuition or what this formula is trying to say, right? Uh, our SS model can also be rewritten then to compare because we want to use the SS residual, right? So it's like 1 minus SS residual over SS total. And the reason why we can do that is thanks to this evergreen formula equation here that when we bring over SS model, SS residual to the other side, SS model is SS total minus of the SS residual, right? Right. So the numerator is SS model, SS total minus the SS residual. So cancel off becomes 1 minus this. And then you can say that this is actually R squared, 1 minus R squared is SS residual over SS total. Right? So we can similarly say that this is 1 minus 1 minus r squared. So 1 minus bracket, right? We have a 1 minus r squared because this is obtained from here, right? That we bring the whole term over to the left and bring r squared over to the right. And we have 1 minus r squared equals to SS residual over SS total. And that's our SS residual over SS total. And then you have this over this because divide by a denominator that is at the denominator becomes the net numerator, right? So times say n minus 1 over n minus k plus 1. So if we have already calculated r squared, we can, starting from r squared and n and k, start calculating the adjusted r squared. Okay, so that's the calculation. But what does it try to say, right? You can get a feel of it by looking at the SS model and SS total because we already have it here. Nothing to do with K. Can you see that? It has to do with N because of sample size. It has to do with Y and all that, but nothing to do with K. But over here, you see in adjusted R square, K is involved. In fact, the larger the K, the lower is the overall R square, adjusted R square. And the smaller the N, again, the lower the adjusted R square. Okay. So in other words, to make adjusted R square high, close to 1, we need to have both this and that, high sample size and small k. High sample size, because we touch reality more, we ought to be getting more reliable value, and this should show up in just R square. Smaller k, because the larger the k, right, the larger the k, you better have even higher sample size. In some sense, it is the ratio of n to k that is important, right? So it's not just net, n must be large. How large is large, right? 30 is large. If I have a sample size of 30 and k is 30 variables, 1, 2, 3 until 30, and you are trying to estimate 31 coefficients, correct or not? Yeah, because B1 to B30 plus B0. That's roughly one sample measurement per coefficient. It's like I measure this, that's my coefficient. I measure that, that's my coefficient. That's ridiculous right now, right? So to estimate the gradient is like a population mean gradient for x1, for x2, for x3. So there are k populations here. And to be reliable in estimating the population mean gradient, it's the same procedure in the one sample confidence interval calculation or hypothesis test. You need to have higher sample size per unknown, right? Per unknown gradient. So if we have sample size 30 and you have 30 variables, that is going to something like saying I just measure one time and that's my population mean gradient. That is certainly not acceptable if you have been studying all the past videos, right? So in other words, the sample size n to k, right, doesn't mean you must not have a lot of measurements, because we did say earlier on we want to decompose, right? So we may have the budget and time and manpower to obtain a lot of measurements from many aspects, from 30 different aspects, right? For the geological site to see if there's oil and gas underneath, and that is a maybe $1 billion business. So we do have the budget, manpower to do all that measurements. So we have 30 different measurements, but we better make sure our sample is what? Very, very high, right? One easy guess is one unknown population mean gradient value should have at least 30, right? So if you have 30 variables, then you better have 30 times 30. So that's 900 measurements. Expensive, but you are talking about a multi-billion-dollar business. So it has to happen, right? That's at least we get a guidance. Sample size of 900 and more, something like that. So when due to the actual location, contextual reasons, whatever it is, run out of budget, the place is so rough that we cannot obtain 900 sample size, then what would be our reliability in terms of the R square? So at that point in time, we want to look at adjust R square. Basically, my advice is whenever you're doing multiple regression, always look at adjust R square. Right? It is a sort of a feels protected measurement of reliability. That is, it doesn't. If you just look at R square, it may falsely let you know that it's a very good model. It's like 0.95, 0.99 even, when actually it is very bad in the eyes of adjust R square. So always look at this and interpret it like as if it is from 0 to 1. Now I say like as if because there are some combinations of n and k such that adjust R square can become negative. All right, in those situations, you kind of like throw away the whole thing immediately because negative adjust R square is just bad, and your R square could show very nice figure like 0.9295. Adjust R square minus 0.5. So bad that it's beyond zero, beyond recognition, right? So one important number to look at, right? Adjusted R square. But of course, to talk about adjusted R square, we need to talk about R square to understand this proportionate nature. Higher the better, and R square and adjusted R square both are trying to give this qualitative figure of amount of fluctuations of the observed response variable. Very important, remember? That is explained by our model. We say explained by, accounted for by. To me, it's like recreated by, because it is a model that induces all those fluctuations, the sum of error squares, or rather predicted value squares, to try to recreate the green squares, right or not? Yeah. So that's the idea. Okay. All right. So that's so much for the two-dimensional discussion. Next, we like to go into the higher dimensional world. So to go into higher dimensional world, I have to fly to the left side of the screen. Okay, so the higher dimensional world, we will first set up the variables. So higher dimensions. Higher dimensions. Because we are talking about multiple linear regression, so we are existing in the higher dimensions. You like it or not, right? So at this point, what is the sort of theoretical support? Does it work? And of course, it better work, right? We will then talk about X. So we actually want to have the values, right? Where y is equal to x, capital X, and my capital X is a matrix now, times a bunch of weights. Actually, I wanted to write beta or the b's, right? So we are trying to find out the weights so as to obtain the measured data y. So here, y is an element of. So in order to distinguish, let me just put an arrow. Okay. So that's a vector. So y vector is an element of, let's say, real numbers n by 1. so that it has some n measurements. N is the sample size, so it looks something like this, one column, and this is n rows. So X is a matrix. It is n rows. Rows will be the samples by k plus 1 columns, right? So it will be this, or rather one, and then followed by other data, x1, x2, x3, columns, right? So n rows and k plus 1 columns. K is the number of variables we have, right? Yeah, because we were saying number of hours of sleep, number of hours of study, and so on. Plus 1 because the first column will be inserted with a 1 to account for the y-intercept. So the y-intercept, for example, in our simple linear case, is just born out, just pop up here, b0, right? So the b0 just pops up. In matrix vector form, we need to have a parking lot for that. So that will be the ones here. And then for the weights w, it will be real numbers, right, with k plus 1 by 1, right? So it's a vector of how many rows? K plus 1 rows, dot, 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 k plus 1, including the y-intercept. So the first term in the first cell here will be the y-intercept, right? So it cannot just pop up out of nowhere. It has to be already factored into the parking lot of the vector itself, right? And we have one column thin. So it's a column vector like this. So the structure looks like this. And oftentimes, whether you use Excel, you use R, or you use Python, right, you will have to present the data to the software best is in this manner, all right? Because softwares are written, the functions are written in such a way to expect table of values, which is just called matrix in math, and table array, two-dimensional array, or what do you call that? Data frame in Python and R, right? So basically, you just have to go through this because this is the mathematical basis that makes things work. So we are going to do this by populating the y vector with the y response variable, the x matrix with our controllable data measurers, right? So we have all this past information, y and x, and we want to basically find the vector w to make it work. So what's the basis to do that? The basis to do that is to find the delta, right? So to find the delta, so that y hat, rather not y hat, the vector y minus the predicted vector is going to have a minimized error squared. Okay, so we begin by saying, let's say we substitute, okay, the y here by beta. So we want a vector y minus x times beta. Okay, so beta is the actual weights. Our weight is computed based on real life captured data, which will have noise and all that, right? So our weights are just point estimation of the actual beta weights. So we have a beta, actually beta is a vector. Okay, bunch of betas, beta 0, beta 1, beta 2, beta 3. And we want to find the error squared. Okay, remember, these are vectors. So vector minus a vector. And then we apply this, what we call a 2 norm, to find the sum of squares. So think of this double absolute sign, right, and squared as sum of squares. So this produces a real number. So we want to minimize this, right? So the goal is least square, right? So least square. So this is the square of the error, and we want to minimize the least square. This can be expanded up as y minus x beta vector times y minus x beta vector. But to do a matrix vector times, we have to do a transpose. Now all these are just vector matrices kind of idiosyncrasies that we have to follow, right? So we want to times them. It's just like square, right? This times this itself. But to make the row and column work, we have to transpose it because this is a vertical column, right? So like n minus the n by 1 minus n by 1, so you get n by 1. N by 1 transpose, you get 1 by n. 1 by n made vector times n by 1 vector, you get a 1 by 1 vector, which is a real number. So this will give us a real number, something that we can minimize. So to expand it out, we will get y transpose y minus, for the sake of brevity, I will just write them out, right? Plus the beta vector transposed. All the transposes, they are to make the vector matrix products work nicely, that's all, right? So if you haven't had a course in products and matrix, in matrices and vectors, don't worry. It's like expanding a quadratic equation. Or it's like a square minus 2ab plus b squared. Except to make things right, we need to add in some transposes and matrix vector multiplications. They are not commutative. So we do have to take that into account. In other words, a times b is not b times a in terms of matrix and vectors, but never mind, right? So we can then obtain this expression. And to minimize, we use apply calculus to this, right? We take derivative dy dx d expression d beta, because we are trying to say what beta makes this expression minimum, right? Like what weight will make the error minimum, will minimize the error. So we are trying to say that d of this thing, d of this y hat, y vector minus x beta vector, 2 norm, this thing over d beta, right? Over d beta vector, right? So it's vector derivative is going to be 2x transpose y vector plus 2x transpose x beta vector. And we want to set this to 0, equal to 0, set to 0. So this is the vector. This is the derivative that shows us the direction of change. We set it to 0 to find that particular combination of beta, and that would give rise to a sort of a zero derivative. And zero derivative can be maximum or minimum, right? And we do know from the context that this would be minimum. So actually we should prove that it is also minimum. But we already can understand from the context that there's no maximum. Y can go to infinity, beta can go to infinity, right? So the only thing that can be found when the derivative is 0 is minimum. So long story short, let's cut to the chase. And the idea is that the beta, we say highlight it. So the beta vector is going to be given by x transpose x inverse. So taking the matrix inverse, which is very tedious when the matrix is large, right? Because we do have a large sample size, right? We do want a large sample size. Also, when we can afford it, then the matrix X becomes large in the size of the table, right? And we need to do the inverse, but fret not. Don't worry. These days, getting the inverse is a function call. Very, very straightforward, right? Transposing is another function call. So this is like one, two, three to four function calls, and then we are done. We get the weights right away. So it's very, very straightforward. But any software will have to be supported, right, by the relevant derivation of theory in order to be able to operate them. So we can just use basic matrices, matrix operations, find transpose, find inverse, find the product, multiply by the vector y, then we are done. As, in a way, as simple as that. Finish. Right? So the thing is that we would then run or call functions, right? And then supply our matrix. In fact, the matrix or the table of data values x1 to xk, right? And then we supply another vector, y1 to yn, not yk, yn. Then now you understand why we actually supply them as two components in most functions, such as R, Python. Excel, of course, is table-based, but even so, you will demarcate very clearly y and x, the bunch of x, a lot of x. You can have a lot of columns for x, but only one column for y, and that's the reason here, right? So all the data and all the y values are being used in order to produce the weight, and this is our W, right? So we will just calculate our W. So this is our W. So one example is that suppose our X, let's call it X0, our raw X is going to be given by some numbers. So 2, 1, 3, 0, 1. 3, 0, 1, 2, 1. 1, 4, 2, 3, 1. 1, 4, 2, 3, 1. And I'm not going to use a lot of space, more because if you are interested, you can see the numbers here, and then start calling Excel to give you a taste of what will be the weights as a result. But here I'm going to kind of show in slow motion how to derive the weights, right? So you can call Excel to derive it. You can call R, you can call Python, statsmodels.api.ols. There's an ordinary least square function, which is very useful and shows a lot of information, comparable information with R and Excel to let us understand the model a lot better, right? So what we want is to prepend the ones here, right? So our measurements are all these columns here, and we want to prepend manually during our calculation to form ones, right? So we will have 1, 1, 1, 1, 1, as many ones as there are sample sizes. Then we copy it. Copying is a very quick and frequent operation in numerical analysis and data analytics, right? So we copy the rest quickly, right, and flawlessly. And suppose our y is like this. It will be captured as 10, 8, 12, 9, and 6. Okay, so now what do? We will want to calculate the beta using X transpose X as a matrix. Take the inverse, multiply by X transpose, then multiply by Y, vector Y. We have to do it from left to right as a rule of the matrix vector calculations. Okay, so but long story short, I am just going to show the X transpose X, right? So then X transpose X inverse, and then X transpose X inverse times X transpose X in order to obtain the weights. So let's just jump right in. So I have the X transpose, which is going to flip, right? So 1, 1, 1, 1, 1, then 2, 1, 3, 0, 1, and all that. Then I have X transpose X, right? Which is going to be 5, 7, 7, 5, 7, 7, 11. Okay, 7, 15, 10, 13, 7, 10, 15, 12, 11, 13. Now, all these will be done through software, right? But I want to illustrate it more like a sort of a sequential steps. So we can, this is X, we transpose it, then we multiply, right? And then we are then able to obtain the X transpose X inverse. That means we just treat this as a V, for example, matrix V, and take the inverse. The inverse of a matrix is a matrix. Sometimes the inverse may not exist. Okay, then in those situations, we will need to do other steps to make sure that we can obtain the weights. Those steps will be a little bit more advanced in terms of mathematics, but again, it's just a function call away. So, but let's understand the basics first, right? So suppose we take the inverse, right? And of course, this is only correctly done through the mathematical understanding that we are headed in the right direction. (0.178) negative 1.033, 0.122, 0.178, 0.279. If you get your inverse for X transpose X like this, then you are on to the right direction. Okay, and our final matrix to calculate is X transpose X. Inverse already, then we times the X transpose itself, resulting in yet another matrix, but this time little bit fatter, little bit wider, right? So minus 0.455. If you cannot see the numbers, don't worry, right? Just you should be able to match one or two figures. It's like matching the lottery numbers, and some numbers match means you are more or less correct, because the numbers cannot be matching by chance, right? Matching a few, if you can match several, then likely the rest of your numbers are correct. 0.136, 0.205, right? Negative 0.364, 0.341, negative 0.045, 0.068, negative 0.182, negative 0.205, 0.227, 0.159. And now you see the guts and intestines and everything, right? The inner organs of everything in the computation process for the population gradients, population mean gradients. Right. So we get these weights, these coefficients in the matrices, right? And one last step is to do this matrix multiply by y. Yeah, because that's our final instruction here, right? Then we will end up getting our beta or w. So our w vector, right, in the program now, so we won't use the arrow, is going to be 1.2727. Now this is the final crystal we are looking for. Also the crystal to see the world. Knowing that initially our K was how many? Can you tell me? What was our k in this example? That's right. We have 3 for our k and 5 for our n, correct or not? Yeah, number of rows is 5, right? We have 3 factors influencing our GPA. We have 3 what we call the uh, features, right? In many modern articles about AI, we'll call them the features, like 3 aspects, 3 perspectives, 3 sets of different, hopefully non-correlated measurements, right? That means you measure 3, they are like 3 orthogonal uh, measurements that would contribute to explaining the y values. And we repeat that 5 times. So our feature set, how many k? 3, right? How many factors? 3. End up our weight or our coefficient, we have 4. Why? Because we added 1 here. So the first one is our B0, and then B1, and then B2, and then B3, accordingly. Right? So this means that our model is going to be y hat is equal to, okay, maybe it's good time to say our y hat is equal to 1.27, this is how we interpret the y, plus 1.9318 x1 plus 1.4091 x2 plus 1.3864 x3. That's it. This is our model. The end of the long march. Right. So this is what we are after. This is what exactly what we are going for after we did all these number crunching, which is not difficult after a while, right? Thanks to the theoretical guidance that even if we have n equals to 100 and feature set will be 10, 20, 50, it will be a big table, huge matrix, but the logic, the times, that's why when you look at the matrix operations, plus, minus, times, divide, dot product, matrix products, matrix inverse, they're not too far away from our original arithmetic operations. And yet it is very scalable, very easily generalizable to higher n's and higher k's, right? So we have big tables and end up we just systematically read off, we straight away get this. Very simple. Okay, so the predicted values, what are our predicted values? So if we pipe in the original x, right? So using original x, predicted y hat is equal to, I get 10.75, 8.75, 11.25, 8.25, and the 6 at the bottom. 6 at the bottom. And it's good idea to, because we cannot see a 3-dimensional world, right? Our k equals to 3 means 3-dimensional world. We kind of like ignore the 1. We added in 1, thus making it 4-dimensional, but that's a artificially induced dimension, so we don't care about that. We just talk about 3 dimensions. So over here, we can then compare it with our original y, right? Y is equal to 10, I better write carefully, 8, 12, 9, and 6, right? And you can see that our prediction is not bad, right? When we test run it using our original x, it ought to be exactly, right? But of course, we know it won't be exactly, but it's not bad. It's very close. Every number is very close. In fact, the 6 is exact, right? So this is a bit similar to our earlier 2-dimensional situation, or rather 1 dimension, right? And then the y is the other dimension. And the line is not bad, right? It's able to recreate most of the squares, right? And so the error is small, but not zero. So same thing here. So of course we can compute the corresponding SS model, SS total, and SS residual, right? To gain a feel of the R square, adjust the R square and all that. But I won't bother you with that because we will run it through Python's stats model ordinary least square calculations, and then we'll get to look at numbers. So your job becomes more to interpret the output tables, as we'll see as an example of this. So we'll use this numerical example literally to pipe it in and then see what is the outcome from the already written function and libraries, and then interpret them. Okay, but to interpret them, we need to also look at uh, some tests required, which is the global model test, variable significance test, and the assumptions that are needed. Right. So we were saying earlier on these three parts. Okay, so we'll look at them one at a time. And of course, I need to first carve out some real estate to talk about the tests. Okay, so there are two hypotheses, or rather two sets of hypothesis tests. I'll just write as two hypothesis tests that are very important for all multiple linear regression exercises. Okay, exercise means the steps that we have gone through. And one is the global model test. Is the model significant or not? So it's an F test. Is the model significant or not? Because if it's not significant, forget about it. Because everyone in the world will be looking at this number, right? So if you publish, think of yourself announcing your test. Hey, look, world, I've just discovered that in order to improve GPA, right, you should do this, right? So first, people will look at your model. Is it significant or not? Did you perform a F test, right? If it is not significant, no persuasive power. Okay. If you are not announcing to the world, you better not trust this model, all right? Because it is trying to say it is not significant. And stick to the word significant. I encourage you to use the word significant. Don't use the word important, all right? So that when you see a large p-value, then you say, oh, it is not important. Maybe you can, as a secondary inference, conclude that because it is not significant, it is, in this case, not important. But it is not always the case, right? So the next one is variable significance test. Variable. Which variable is carrying the biggest weight? Is a t-test. Just so you know. Right? Because some reports, right, some analysis reports, Excel, for example, will say that the following are the t-test statistics, and you wonder why, because it's a t-test. And that's testing for variable significance. Okay, so for the first part, the global model t-test, right? So the global model t-test, the global model f-test, the goal is to see if the model is significant or not. So that means that we'll write down the hypothesis, right? The hypothesis will actually explain quite a bit, where it says for H naught, all the gradients, all the coefficients and gradients, right, equals to beta k, they are the same and equal to 0. So, which is another way of saying model is not significant. All right, and this is fixed, always fixed, always fixed. A little bit like ANOVA, right? So, and H1, at least one of the beta i's, right, is not 0, which means at least one of the measurements is able to try to recreate the fluctuations observed in one. So it's like I have a team of K people trying to carry a heavy weight. Maybe it's a boat, right, or sail or whatever it is, right? Carry or some furniture. Um, if the if everyone lifts it up and then cannot move, then is the team effective? No, right? Let's say carrying it up, lifting it up. If the is the team able to lift it up and move? Well, team cannot be moving. That means not enough strength, right? So whole team is not helpful, not useful in moving the boat, moving the furniture. But if the boat or the furniture, heavy furniture, is being lifted up and is moving towards the destination, maybe the seaside or the room, is the furniture, is the heavy object moving? Is the team useful? Is the team functioning? Yes, yes, right. But actually, if you look at every single one, someone is just pretending to lift the weight, but not touching the boat, right? So obviously not contributing, right? But is the team, you're talking about the team, is the team useful in helping the organization or or you to move the furniture, to move the boat? The team, yes, as a whole, right, as a collective. There are some slackening of people inside the team, but the team itself is useful, right? So that's why we want to uh, talk about this. Now, why do we associate it with gradient equal to 0? So in other words, when gradient is 0, all the gradients are 0, what does that mean? When all the gradients are 0, if one of the gradient is 0, it means that we have this case, right? This will be repeated for k number of graphs, but I won't draw all of that. So this is the y values as the rather for xi, sorry. So for xi, when xi changes, y doesn't change, right? Implying that the gradient for beta I is 0, right? Now, so as xi increases, y doesn't change just due to xi increasing. Then in that case, mathematically the gradient is 0, right? But then inferring back into the reality, what that means is if I increase the budget or I reduce the budget, the sales is the same. That means the budget is not a factor in explaining why there's good sales or bad sales. If I increase the number of assistants to your team and I reduce the number of assistants to your team, the sales is the same. Then you're telling me you want more assistant. Then it doesn't bring out that significance, right or not? So now you can understand, right? So we convert that real life complicated negotiation. Hey, boss, I need more assistance because my team is enlarging. Having more assistance will help the sales. But then the boss has this information, right? That the number of assistants, xi, and the sales, y, the gradient is 0. So having more assistants, less assistants, no change in sales, right? Because your sales is all done by online sales or whatever it is, right? So don't come and bluff me and want more team members under your group. So, politicking. As opposed to something significant, whether downwards or upwards, right? So let's try the upwards. Okay. So this will be the case when beta I is not zero, right? If I give you more assistance, your sales actually goes up, or overall company sales actually goes up. Even though I don't know why, right? Your team is a small team. I give you more assistance, somehow the company-wide sales goes up. Very strange. Or because there's a wizard, right? There's a social media influencer, right, in our team. That's why the effect is very huge. Right? Something like that. I don't know. We don't know. I'm just creating excuses, but that is not yet proven, right? So if there is a slanted gradient, right, then it would be the case that this number of sales assistants is significant factor in helping to influence. Of course, the influence can be bad, can be negative gradient also, right? But helping to influence the Y, very important, Y response variable. And in the case when you have k dimensions, all of them are zero, then literally all are stagnant. No matter which variable you change and tune and increase and decrease, the sales, the Y response variable, doesn't change. So all the variables that you have guesstimated, that you hypothesized would have accounted for the sales fluctuations, now results in the entire model being not behaving, not changing at all, no matter how you tune those tuning knobs, right? But if at least one of them is reacting, then this collection of variables, maybe the rest are all zeros, right? So maybe, or close to zero. But this one is so strong that itself is enough to explain everything. Then is the whole collection still meaningful, still significant, that is, in accounting for the Y? Right? The question is about the whole set of variables. So if we reject, then if the p-value is very small, then we reject h naught. By now you should understand that. Then the model is indeed significant, right? Because as a collection, this collection of measurements allow me to predict very well. All right, so R squared is very close to 1. So it has to reject first, right? All multiple regressions have to go through this rejection of the null hypothesis that model is not significant first before anything else. So that's why this global model t-test, global model f-test is very, very important, very significant, right? And of course, in retrospect, if we say, wow, only one variable is significant, right? Then why do we include the rest? Right? So for example, if only the number of hours of study helps to increase my GPA, then why do I include number of hours of classical music listening, number of milliliters of juice I drink? Why do I do that? Of course, that's after the fact, right? After you did all the data collection, you do the number crunching. The report analysis gives you a p-value, and you reject, right, to find that the model is significant because you did use the hours of sleep. This test doesn't tell you the rest of the variables are not important or which variable is important. It only tells you the whole model presented as this, right? The whole model is significant. Therefore, keep them first. And if you want to microanalyze which variable is doing the job, then variable significance test comes in, right? And remember, at first, we don't know, right? We don't know. So we put in our best guess. Our best guess is number of hours of sleep, number of hours of study, number of friends we study with, though all seem pretty relevant, right? So we put in and we are investigating. We don't know. And that's why after performing a global test, right? And in many cases, you will have multiple variables. Therefore, you should always look at the variable significance test. So in variable significance test, our goal is to test for that particular variable, right? So for that particular variable, is it significant or not? So H naught will be for beta I equals to 0. That means that variable I is not significant. For the same reason that it is having a 0 gradient, right? So the graph is the same. I will then share, right? That the graph is horizontal, and no matter how xi changes, times a 0 is always 0. That's the reason why, right? So the y is going to be not changing, just based on the b0 constant. Versus if I reject, then my beta I is confirmed. Statistically not 0. Okay, so variable I is significant. Of course, we would like all our variables, hopefully, to be significant. But, right, there's always a but. We don't know. To begin with, we guess, based on our best conjecture, the variables that should participate in accounting for the fluctuations in Y, our GPA, our company's product, our employees' productivity, and so on and so forth. But, right, which variable ends up being the one that's significant? Okay, so what we do is we do two things, right? We look at this and we look at this. We look at this because we have many variables, like the GPA. We have hours of study, hours of sleep, hours of classical music, and milliliters of juices. So many, right? If suppose in reality, from psychologists, from whoever, right, doctors and whatever medical studies, only, oh, is it true? Hours of study contributes to your GPA, not any other factors. Suppose that's the case. How do we know? Right? So this global test tells you the whole set is significant. So we keep, then we say, okay, we have so many variables. Which ones are the ones that are workhorses? Workhorses means they do the heavy lifting. They explain the fluctuations, whereas the rest just showing the action of carrying the boat, right? They are not actually doing the job individually. So if we have 10 variables, we'll do 10 such tests, right? Some will reject, some will not. Reject means, yes, that variable is really lifting it up, all right? And very, very small p-value. So we can actually look at a little bit more at the extent of the p-values. Now you notice that up till now, in all the tests, I haven't been talking about the strength of the significance. Because in many cases of the earlier tests situations that we use, we are not trying to use the strength or the degree of significance to in our daily communications. We're just trying to say, hey, you know what? My COVID-19 new drug is efficient and effective. Look, p-value 0.0005, right? But yours is 0.0008. Oh, so mine is a little bit better. But we can't compare to that extent, right? So long as it's significant, it's good enough to say, you know, mine is good. But right now, we are doing this in entirely the same context because it's the same set of sample data, right? Obtained through the same period of time, and all the x1 to xk, they are kind of like synchronously paired with y. They are captured based on the same item, same person, same geological exploration site, the same object, the same company, right? And so the context is the same. And then the p-values are analyzed in one shot in the same calculation. So it is then mildly meaningful to compare the p-values because p-values are, after all, probabilities. Mildly meaningful because when we compare probabilities, unless it's drastically different, you don't try to micro compare, right? Like p-value of 0.045 is better than p-value of 0.046. Here we use our subjective rough comparisons. So p-value of 0.0002 is better than p-value of 0.02. Both are significant at 5%. 0.05, right? But the 0.0002, the many zeros too, is signaling that, hey, it's doing a lot of work because it's number crunching in the same matrix and calculations. So resulting in a p-value that is so tiny, right? That it is contributing a lot. It's like, I'm doing a lot, something like that, right? So we can understand it in that sense that when the table of p-values come out in a typical summary report by any software, Excel, R, Python, the p-values will then be mildly comparable. And then we can get a sense of, okay, first of all, which are the ones that are definitely out? P-values of 0.7, 0.8, 0.5, 0.3 even, right? Like 30% chance, then they're out. Those that don't pass the alpha equals to 10%, let's say, right? So they're out. So do we strike out any, right? And suppose going forward, because we are trying to generalize it, right? So you might have the budget and luxury to do 10 variable decomposition, 10 variable exploration, 10 variable investigation. But we want to like push it out to the either the general public or the officers or the families, right? Because you're doing some sort of health kind of test, right? So you cannot ask individuals or families to measure, then try to predict your health, try to predict your heart rate, right? So there's this formula, right? What's your maximum heart rate? So online you will find that a person's maximum heart rate is something like 220 minus the age of a person. Well, easy, right? Easy enough. But does it work? Are we all robots that are exactly having that heart rate? 220 minus your age, finish. So your heart rate is like a mechanical robot that is highly predictable, engineered to be totally following that formula? No, of course not, right? So likely it would have been many variables participating in that. So maximum heart rate of a person is a statistical variable, right? Kind of like uncontrollable. Remember, expensive and important, expensive to measure accurately. But the others like age, very easy, very accessible, right? Constants 220 is the y-intercept. Maybe there have been other variables in the actual expensive, highly funded medical studies, right? So perhaps your alcohol intake per day, average alcohol intake per day, the amount of proteins you eat on an average of daily basis, but who can measure those, right? Or not? Much less to say accurately. So with a highly funded medical studies, you can have all the other variables inside. Uh, Number of hours of sleep down to the minute, and then the REM sleep duration, the deep sleep duration. You can have all the expensive medical equipment to measure brain waves. How do you expect a normal, general public person trying to improve cardiovascular health or health in general? All these things, right? All these variables. So to provide a model and say, look, this is government funded. We are going to share this complicated model, but very accurate and highly predictable model with the public. Please use that, right? It's kind of like useless because people don't get the equipment. So which one? Now you come down to the variable significance test. So they might say, okay, of these, like amount of protein intake, amount of alcohol intake, amount of water, number of hours of sleep, number of REM minutes, and all that. Which one is the most significant variable so that I can like truncate this model and educate the public that, hey, you know what? Your maximum heart rate is this, therefore you should pace yourself and do the right amount of exercise, right? Something like that. So they can then look at the significance level and say, amongst all these variables, age has a smallest p-value. Okay, let's just use that because that is doing the greatest amount of job in trying to estimate the maximum heart rate, given that various people have different build, athletic ability, DNA, circulation, whatnot, right? And that's why a simplified model might be better. So don't sort of seek always for more is better, right? Accurate is better. In practical applications, what works is better, right? What saves costs and works with high quality and reliability is better. You see, the considerations are different. And we use all the mathematical tools, analysis reports, tests, values, and all these to help us achieve that. Okay. All right. So, in summary, any multiple linear regression that you do, you must look at these two tests, right? The p-values, and you must look at adjusted R squared. Okay. Then you can decide which is how to move on, carry on with the use of that model. Okay, let's draw a line here and move on to the second last part of our discussion, which will be the assumptions. The assumption, right? Just like any other theory in mathematics, we always start with some assumptions. You should know the assumptions because the assumptions underlie all our calculations and, as a consequence, underlie the validity of our conclusion. So if we break the assumption, then the conclusion is wrong. Okay. Did we accidentally invalidate our assumption, any of the assumptions, right? So during our calculations, during our interpretation of the outcomes, if we did, then we better be careful, right? Because sometimes certain invalidation of the assumptions is not that serious. It just means that the outcome may be a bit fuzzier, but we're just saying go or no go. So being fuzzier doesn't really change much. Sometimes, even if sometimes we have no choice but to invalidate the assumption, right? Because in practice, it's just too expensive to adhere to all the assumptions. So we need to be clear. What are we treading on? Right? Are we trespassing into forbidden territory and not knowing it and say we are innocent, our outcomes is still valid when actually it's all wrong, right? So at least when we know we are not adhering to the required mathematical assumptions, we find ways to make sure that our kind of incorrectness in the assumption is not that serious, right? Or else we will take a very careful interpretation of the outcome, knowing that it will be fuzzy, so that we can announce it or publish it or convey it to our boss, customers, and colleagues, right? With some qualification, right? Trying to say that we did do our work and I don't want to mislead you, right? So it does break a little bit or occasionally, right? This assumption, right? So what are the assumptions? First thing first, and in no particular order, is that y is linear with x. All the xi's, right? The matrix x. Y is linear with x. That means inherently, down to the core nature, y is indeed behaving like proportionately with x1, x2, x3, x4, x5 until xk. But as you know, our real life hardly will be everything proportionate, right? The more variables you put in, the higher chance that some of the variables will kind of interact with y in a non-linear way. Maybe the more the worse. The little, the more. That means little values of x7 increase x7 by a bit, y increases. But over certain limits, increase x7 by a little bit, y decreases, right? So that becomes non-linear. It changes direction. But we are just going to assume, we have assumed that y keeps on increasing forever and ever and ever. That's why you see that the x values must have a limit, knowing that in real life, no measurements will keep on increasing and no response will keep on increasing forever and ever, right? Um, without limits, like till infinity. Nothing goes to infinity in real life. So that's why we need to make sure that when we're doing multiple linear, right, linear regression, knowing that linearity will bring us to infinity or minus infinity. So we better make sure our range of x is really, relatively speaking, small. Okay, what is small is relative to other x's and the y values, the change in y values. If y changes by a lot, by twisting x from 1 to 1.01, then your small better be even smaller. Like you change x by 0.0001 at a time, right? Something like that. But if x changes little bit only, like stock price changes by 1%, 2%, whenever companies' profits goes from 1 million to 2 million to 3 million, right? It's like not responding too much, even though it's 1 million increase in the profit, right? Then you better have you may have, right, 1 million to 10 million, and because then the y will fluctuate. That means the greater y is more, right? So that's why this assumption is very important to for us to design our measurements, our experiment, so that we don't keep on going into larger and larger values of x, that y starts to misbehave, right? And then we have problems. No multi-collinearity. Multi-collinearity. So collinear means the axes themselves linearly regress with themselves. Right? So the x2 is proportionate with x3, the x5 is proportionate with x7, x8, and x9, that kind of meaning. And we have x1 to x10. So if they themselves are proportionate with each other, like for example, number of hours of study and number of hours of sleep, right? So if we start measuring over a prolonged period of time, larger than 24 hours or near to 24 hours. Prolonged, why? Because it is the case that one day is fixed at 24 hours. So if you have something close to 23 hours, 24 hours, 25 hours of study, right, of measurements, your number of hours of study is measured over one day's kind of situation. You include these two variables, right? Number of hours of sleep, number of hours of study. Knowing that, let's say the rest of the meal time and whatnot, they don't add up much. You are a nerd. You're just only studying and sleeping. Then number of hours sleep plus number of hours of study equals to 24. That means they are linearly related. The more, the less, right? The more you study, the less you sleep. The more you sleep, the less you study. You know it already. So then we say that the two variables are said to be having multi-collinearity. Actually, two variables will be collinear in that sense, right? One is predictable by a linear equation or from the other. And if you have multiple variables participating in the same equation, like x3 is equal to 2 times x4 minus 0.5 times x5, now multiple variables participating in predicting for x3. And they're all on the right side of our model. They're all on the right side. That means these guys, they're colluding, right? They are linearly proportionate to each other. They are like, each is predictable by the combination of one or several of the others. Then you have a problem. They themselves form a linear regression themselves, right? And then we have an issue. The y values that will be predicted, the weights themselves will not be accurate, right? So then we have a serious problem. Even if it says model is significant and everything, we better not trust it, right? Okay, so that is one thing that we are assuming. In some sense, the better be that all the variables are independent. X1 is independent of X2 is independent of X3. That's why some books call these x1, x2, x3 variables independent variables, right? As I said earlier on, I really frown at it. Very scary because usually in practice they are not, right? And what if you have multi-collinearity? Then we say that these independent variables, they are dependent. X3, the independent variable of x3 and x5, they are dependent. What do you mean, right? Very confusing. But we don't want multicollinearity. We're assuming that there is no multicollinearity. Okay, so that is saying that x3 cannot be linearly predicted by any of the other xi's. Any. Okay, any at all. Of course, no multicollinearity could mean that x3 can be predicted by x5 and x6 in a non-linear way, right? So, but this is usually strong enough. The best is all the xi's, they are independent of one another. All right, they are all not connected, predictable, influencing one another at all. That's the assumption. Okay. Next is the residuals. By now you understand what is residuals. The residuals, right? They are the errors. They follow normal distribution with a mean of 0 and a variance of sigma epsilon square. That means a constant variance. They are normal in nature, right? So the residuals need to hover around, right? There will be residual. We acknowledge that there will be random noise. There will be, equipment measurement noise due to the existence of nature, right? So it's natural, right? And we accept that. Accept that the errors better be normally distributed. What are the errors? The errors are all the numbers resulting from yi minus y hat I, right? Yeah, so that's the residue we talk about. The residues, when you plot them as a histogram, better show up as approximately a bell curve. That's what it's saying. And centered at 0. Now what happens if it's not centered at 0? Like centered at +5 or just magnify +10. If it is +10, that means the errors have an average of 10. Which means that the 10 ought to have been captured by your y-intercept, right? To raise the value of y to 10 or by the y-intercept of the model. So that's why it's if after the y-intercept is calculated, you still have an error that is +10. Usually not that big. Usually maybe if it is non-zero, then it is maybe not that big, because if it's that big, then your y-intercept is very problematic. Then there's some problem basically, right? So we want the error to be centered around 0 so that it adds nothing to the model. So essentially there's a plus epsilon behind. So there's a y hat, right? And it's true for all the predicted points. But if you want to predict or touch the data, if you want y hat to become yi, then you better add an epsilon, because the noise is the gap there, right? So if we add epsilon, that epsilon better show no bias. In other words, the average is 0. Okay. Next, we want to say that the residuals are homoscedastic. Sometimes K, sometimes S, sometimes C. Depends on whether you are, I guess, American or British, right? So sometimes you use K, sometimes you use C. Homoscedastic, just a bombastic word to say that the variance is homo. Homo means the same, right? So the variances are the same. What does that mean? Not equal variance. Yeah, equal variance in some sense, but equal variance. As we gather the residuals, the residual variances don't change. Okay, the residual variances don't change as we go from measurement to measurement. So this part is more like trying to plot out the residuals. That means we calculate the errors, right? When we increase the value of x, going from small to large values of x, xi, for example, pick one axis. When we do that, the residue error, which is a real number, wouldn't try to show a pattern. That's another way to think about it. Right? Because variance we can't see directly until we have a lot of dots, a lot of error dots on the scatter diagram. But one way to think about it is that as we increase the value of x, we do the sliding, right? The error doesn't like go in a very predictable waveform. Then if it's like just showing noise, okay, then that's fine. Typically an indication that it is homoscedastic, right? The variance is the same. But if it is trying to say large and small, some sort of a waveform, some sort of a identifiable pattern, then it's likely that there is some sort of a controlled variance there, then it is likely not homoscedastic, right? So we are assuming that. Why? Because of this term, right? We are assuming that this epsilon, the whole population of residuals, including those measurements that we didn't measure, they themselves have a constant variance so that we can analyze this variance and all that. But if this variance changes with the values of x, any x, x1, x2, x3, doesn't matter, right? So that the larger the x values, the larger the variance. The smaller, the smaller. It could happen. I give you an example. If you stay far away from school, from campus, the time of travel from your home to campus tends to vary a lot more than those who stay close. Let me say again. If you're not staying on campus, you're traveling, right? So some of you drive cars, some of you, even if you take public transportation, take a Grab, take a MRT bus, the further away is your destination, the higher the variability. Not only the travel time is larger, but the variability is larger. In other words, if you're far away from a place, you tend to arrive way earlier or else very late. You tend to, of course, you try not to, but you tend to arrive way earlier. Still have half an hour to go. Oh no, I came like 1 hour before the start time, right? It's that kind of feeling. Or you came and then it's already tea time, right? Halfway through the seminar or whatever it is. You tend to be very extremely off the required time of arrival than those who stay near or than those who travel near to their destination. So if your conference location is just next door, you tend to, not saying all the time, right? You tend to be punctual, more closer to the starting time than those who travel far. That is a kind of situation where if x is the distance from starting point to destination, right, then increasing x leads to higher variance, higher fluctuations, higher variability of the both duration of travel and time of arrival, right? Yeah, those who stay far from your office or your campus, you will understand that, right? Because for me, I also experienced that. Right? So I have to travel far to reach campus, and the variability can be very high because of the distance. Anything can happen, right? You start off the journey, perfect weather, then halfway through because the travel duration is long enough for the halfway through to make sense, right? If it's a 5 minute journey, then there's no halfway through. But if it's a 1 hour journey, then it can mean that halfway through suddenly it starts raining, or your part of the location is not raining. As you travel through, you encounter huge rainfall, right? And because of that, consequences happen. There may be days when huge rainfall, nothing happens. There may be days when light rainfall, multiple accidents happen. Then you get delayed, not of your fault, but it just happens, right? So you have more Murphy's Law applying to you when the travel duration is long or you stay far away, right? Something like that. So that is one very, very sort of commonly encountered situation where the residuals, the errors will not likely to be homoscedastic, right? So then we want to be careful because this is a core assumption of errors having similar kinds of fluctuations, no matter which xi is being slided, being increased, decreased independently of others. And the last one is that the residuals, also about residuals, are independent. Independent. In some sense, it's like the each residue being big or small is not affecting the next residue to become big or small. No interaction, no influence, or is it not, right? So we are assuming that there is none, because then it makes all the theoretical derivations easier, right? So we don't have to worry about, hey, what if there's influence and strong influence, then what happens, right? But having said that, we have made this assumption in our derivation. But if this is not respected in practice, then we have a problem, right? So this is a little bit more serious about the residues being not independent, because in practice it also tends to imply that the variables themselves are not independent in the first place. That's why it resulted in this. Right? It tends to imply, it doesn't mean that it proves that this is the case, but we want to be very careful here. Okay, so we want to check, and the way to check is possibly that this can be done by a quick y versus xi scatter plot. Okay, so this is more like a visual check. Then we can, so long as we kind of see a line in each case, that's fine, acceptable. Again, partnering our eyes as a quick linear regression tool. No multi-collinearity. So this way, we tend to use the VIF, variance inflation factor, as a means to detect, right? So this is another subject of discussion, but you can just run functions to obtain this for the xi's. Essentially, the idea is to use x1 and then linearly regress, multiple linear regression with x2, 3, 4 until xk. Then we obtain the r squared. Okay, this r squared. Where's the r squared? The r squared over here. Right, so then we use x2 and linearly regress against x1, x3, x4 until xk. Then we take x3, linearly regress with x1, x2, x4, 5, 6 until xk, each time taking out the r squared. Right, so we want to look at all the r squares. If the r squares are very, very close to 1, or rather 1 over 1 minus r squared, to get the VIF, the variance inflation factor, because r squared is some sort of variance in approximation. So, and to enlarge, because when r squares are close to 1, then that gap, right, will be magnified by using 1 minus r squared. So when we do 1 minus r squared and take the reciprocal, we get the variance inflation factor. We can then see that, hey, which one, right? So x1 to xk all will generate an r square, right? So which one, when you linearly regress against the rest of the exponential variables, has a very large r square, close to 1. That means it is very predictable by the rest, right? Then we might want to. But then it may not be by the rest. So x1 linearly, multiple linear regression with x2 until x10. So maybe not all the x2 to x10 will predict x1. Only x3 is the culprit, right? So if x3 alone, it will be 1 or 0.99. But then mixed with x2 to x10, it probably will reduce r squared to 0.7, 0.8. That's why we don't just look at the r square value itself. We want to look at some range. So like 0.85 and above, we will do the cutoff. So the cutoff is subjective, yes, right? But there's some sense of agreement, right? That above certain cutoff, then they are too strongly uh, collinear with each other that we probably have to reconsider dropping some of them. Also, we can then solve and continue. Residues are normally distributed. Of course, you can test the residues. Hypothesis test, normality test, right? The residues. And for this, we can use various tests, such as what is called the Jacques-Berra test. Or of course, you can also extract the residues and then use Shapiro test, right? But of course, it's all up to the experimenter, the statistics preferences. Then you can also have omnibus tests to test for normality, right? So basically, very important assumption to ensure that it is normal, but then a little bit off normal tends not to be that serious, right? So we're not that um, we're not going to scream that much. Let's put it that way, right? Even when it doesn't pass the normality test, more because if it's slightly skewed, in practice, nothing is perfectly normal, right? And even if it fails the test, it means it's skewed. And if it is skewed not by some strong extent that we will frown, then we probably will just go ahead. But multicollinearity, that's going to be very, very strongly influencing our outcome or affecting our outcome. So is this. So if it's not linear, then we may not be using the right model in the first place, right? So we should be using the non-linear model. And so that will be also very serious. Residues are homoscedastic, right? In this case, we want to also perhaps quickly plot a sort of a residual versus xi plots, right? Just to see that the residuals, they are basically fluctuating the way they fluctuate, right? And not showing some sort of a pattern. Like going larger x, errors going down. Smaller x, errors going up. Or goes down, then goes up. Right? Some sort of a pattern will be problematic. So we want to see no pattern. We want to see white noise. And residues are independent. This one, usually we can, by contextual argument, by our understanding, by our assumption. That means we kind of like, oh, I do know enough of the measurements that they are independent, right? Or rather, like common understanding. So, look, the number of milliliters of juice I drink and the hours of sleep should be independent. Well, I just drink what I like, right? So, but of course, sometimes when we do understand a bit more, it could be that the more you drink, at first it's independent. But after 1 liters of juice, because it's so sweet, you start to feel hyper and you cannot study and you cannot drink, cannot sleep. So the number of hours of sleep will be lesser, right? Then there is non-independence, right? And because of that, residues tend also become not independent. Then we have a problem, right? So again, it has got some ties to multicollinearity, but here, usually by contextual understanding, we can sort of wave hand a little bit because by and large, nobody can ensure everything is independent of everything else. Then you better live in the space in the universe, right? Outside Earth. And you're totally isolated, then yeah, even signal will be independent of each other. So certain assumptions are very serious and deadly if violated, right? But certain assumptions we can wave a little bit and just be cautious. But no matter what, you, right, the person in charge, needs to be aware of what, private space, what violation of the assumptions you are trespassing. So that when you are being checkmated, or when you're being cornered, hey, did you ensure that? Then at least you have something to say, right? Okay. All right. Looking back at our, let me move myself to the right again. Looking back at our agenda, we covered everything. And the last part, I'd like to show you the sample run of the very same numerical model that we discussed and we calculated manually. In fact, you can do the calculation using calculator, right? A bit tedious, but you can try to do that as an exercise. Maybe not the inverse. The inverse really takes a little bit of persistent will to do this at this level. Maybe 2 by 2 matrix is okay, but 4 by 4 is really a challenge. So we can at least do it manually using matrix multiplication and matrix vector multiplication. But let's check our results. What's our result? Our result is the set of weights, right? Against the output from Python's library, the stats models .api ordinary least square, OLS, in capital form, right? So this will produce a result, a model, the ordinary least square model. So if you use that to calculate and then do a summary of the results, right, we will see a table-like output that is very similar to the table-like output of R, right? If you use LM function in R, or in Excel, if you use the linear regression function click, everything is in Excel is click and go, right? Under the data analysis module. Okay, let me turn on the output for using the OLS, right? So the OLS function in stats models.api gives us this table. I don't want to reduce the size of the window too much because then it may not be visible, right? So I know I'm covering some of the numbers. First, let me move around a little bit, right? So they are there, don't worry, right? But let me just quickly walk through. The most important part, right, will be the output. Do we get the output, right? So comparing it with our results, can we see the results? Yeah, this one is the result, isn't it? Over here. So not bad, right? We do get all the coefficients to 4 decimal places, correct? But you can see that so these are the coefficients. You can see that we get a lot more numbers, than just the coefficients. And remember, we got to check the global test first. Because if not, then these are just gibberish. They're meaningless. So let's check. Where do we check? Well, it's over here on the right side. Okay, so first thing first is the f-test statistic and this p-value, which is at the bottom here, right? So it says that the model is not significant. We are unable to reject the H naught because p-value is very large, right? And what is the alpha doesn't matter because it's so large already. Whether you choose alpha to be 10%, 1% doesn't matter. It's just 41.9%, right? So it's way larger. No need to ask what is alpha. So basically, our model should be thrown away. So, of course, because it's random values. Okay, it's just simple integer values, of course. So look at this number. Yeah. So if it is like this, then we are, we have to bite the teeth again and say, okay, fine, let's try something else. Okay. Next is, of course, the variable test, but we'll before we jump off this, let's look at R square. R square and adjusted R square, yeah? In this case, you can see there's a big difference. One is looking very promising. The R square is 0.888. Wow, not bad. The other one is adjusted R square. Wow, what a big hit, right? Big penalty applied because our sample size was 5 only. Yeah, so sample size was 5 only. Not very, not very good. Furthermore, we have 3 features. We have x1, x2, x3. We have 3 mouths to feed, 3 coefficients to estimate. Right? Actually, 3 plus 1, right? Plus the constant y-intercept. So you only have 5 coefficients. So just looking at one coefficient is like the population mean value of the gradient for x1. By CLT, we will need at least 30, right? And you have less than 1, 1 plus. Not enough, right? So no wonder adjusted R square says, hey, that's BS, right? Don't claim this high flying number. Huh? Wrong. So that's actually very bad. So very, very helpful. Next is log likelihood, AIC, BIC. All these are trying to tell us, using different measures, how good this model is. Okay, maybe you say, hey, wait, I thought the p-value is already good enough. This p-value is the model p-value. Is it significant or not, right? You cannot compare this p-value with another multiple linear regression. Then you say, why do I need to compare? Right? Why would I have another? Well, you have another because you might want to say, let me remove x3 and then run again. Let me remove x1 and keep x2, x3 and then run again. Right? Let me try only x1. So all these are multiple models, but they are all related in that sense, right? So should be comparable. Unfortunately, the p-value would be calculated under different computation, so you mathematically cannot compare those p-values. But log likelihood, AIC, BIC, they are constructed in such a way that you can compare these values. For example, the AIC, archaic information criteria. The smaller, the better. So right now, one number, we can't tell. 18.20, we don't know whether it's good or not good. But if you, for example, say, okay, let me try to remove x3, run the model again, get another AIC. And if that AIC is 12 or sometimes even negative, like the log likelihood, then it's way lower, right, than 18.20, then that would be better. So that would be useful as a comparative exercise, but p-value is also very useful for us to assess whether this model alone, standalone style, is meaningful enough for us to carry on or not. Okay. Sometimes we are unable to try to remove these variables. For example, maybe it is a social setting, maybe it is a stated influencing factor. We are trying to investigate whether these influencing factors are affecting or not affecting, and affecting by how much, how strongly, and all that. So we cannot try with other models to remove. It would basically be disobeying the original stated goal of the whole experiment. So sometimes we are unable to remove. Then with AIC and BIC and log likelihood, you are then kind of left in the lurch because with the number alone, you cannot do anything, right? You need to compare with other AIC values. Then at that point, the p-value will become very useful. Okay, all right. So at the bottom, we have these p-values, and they are very useful. And that is to answer our second test, which is a battery of tests, right? So the second set of tests will be once on each coefficient. That is x1, x2, x3. So this is like beta 1, beta 2, beta 3. So unfortunately, all are large p-values and they are not significant, right? So all can be thrown out. But which one is doing more work? Okay, maybe we can say this. Okay, because it's at least lower than others. So maybe we can try thinking of a model that keeps x1, maybe by alone, because x1's contributing power is being eroded by others. So let's try that, maybe. And wait, you say, you just told me p-values cannot be compared. How come you're comparing? Now, these p-values, they are computed under the same context, right? So in a way, like I said earlier on, they can be mildly compared to see which one is carrying more of the heavy canoe or boat or furniture's weight, right? Who is contributing more? I want to keep that guy, right? This guy is just pretending and walking hands free, right? Not really contributing to lifting the boat. Then maybe I should discard x2. So I keep x1 and x3. I try. So various combination. So if you have 10 variables, then it's 10 choose 1, 10 choose 2, 10 choose 3. Many, many, right? Many, many. Essentially even 2 to the power of 10 models to try, if you really want to exhaustively try them all out. But of course, we can do a quick pruning of the less contributing variables. So you might want to like first remove those with very large p-values, gone, right? And then try the rest. Okay. Now, I did keep saying about the coefficients and didn't talk much about the y-intercept. Typically, we don't care much about the y-intercept. Even if it is like, in this case, very large p-value, we are not too worried. So that when it is insignificant y-intercept, we are less worried about that because y-intercept basically is an offset of the the overall y values, the response values. The larger the constant term, the y-intercept term, the overall y values will be bloated up, right? Lifted up. Like it's like an offset. So we can also always minus out the constant term to center the y value. So y is on average at 0, right? So we can reduce the y curve by zeroing the y-intercept without changing the gradient. So that's why the gradients, right? The gradients here, they are much more important in telling whether the factor xi is influencing y or not. Much lesser will be the y-intercept. In fact, no effect at all, right? So we're not too worried about it. The t value gives rise to the p values. So they are kind of related, and most statistical tables for multiple linear regression will show you the t values. But we typically just want to do a quick look at the p values for variable significance tests. Okay. Then typically there's confidence intervals. It's like, for example, x3's gradient, this 1.3864, right? How confident are we that the gradient is this? A 95% confidence interval, if you remember confidence interval, right, is that our estimate 1.3864, right, is having this interval. In other words, the true population mean value for the gradient for x3 lies somewhere between minus 8.68 to 11.45. Not very helpful, huh? Too wide a range. Right? Furthermore, it even goes into negative, so I don't even know whether it's good or bad, right? It can be bad, it can be good. So very, very useless in this case. So it does give you another gauge, right, of a confidence interval. And typically 95% is fixed. There's really no need to change it. But if you want, there is standard error. You can compute your own confidence interval, right, by having the critical value for t multiplied by standard error, right? That will be the margin, right? The tolerance, and then you use the x bar, which is the sample mean estimate of the point estimate of the population mean plus minus the tolerance. You will be able to get whatever confidence interval at whatever confidence level that you want. Okay, the omnibus and the probability, the p-value for omnibus test is to test for normality. All right, normality of what? Remember here that one of our important assumption was that residues are normally distributed centered at zero, having a constant variance, right? So this normality of residues will need to be tested. One test is the omnibus test. Omnibus test looks at the errors directly and check their kurtosis and skewness. That means their kurtosis is the fatness of the tail, right? Does it look like the fatness of the tail for normal on both sides, right? So if they do, then likely it's also symmetrical. But it also looks at skewness. So if skewness is nearly zero, like normal, then very likely it is looking like a normal shape. So omnibus test, that means multiple tests, looking at skewness test and kurtosis test at the same time. Now you don't want to test them individually, get two p-values, and then try to combine them because you cannot average p-values, makes no sense. And you incur error some more when you try to combine the rejection, non-rejection, and all that combinations, right? To deduce the true meaning of is it looking like normal or not by combining two subtests. So the omnibus test combines them internally already, taking into account the various possibilities. Maybe you have fat tail but zero skewness. So is that a normal or skewness is slightly plus or slightly minus, but tail looks like normal. So what's going on, right? So yeah, you can have various uh, histogram shapes that might distort the skewness, but the tails look like normal. So to what extent of deviation do we then conclude? Then we got to perform a simultaneous test. So you can look at omnibus test as another meaning of for simultaneously testing for skewness and kurtosis. Okay. The uh, Jack Barra test is also, and the associated p-value below is also another test for normality, right? So from another perspective, it examines the residues, and then so just like we have multiple different tests for normality in the normal data case. Here, looking at the residues, because the residues are generated after the model is formed from the original data supply. So there are a lot of numbers, right? The original data plus the predicted values plus the residues resulting from data minus the prediction. And there's so much information there to try to give us a sense of whether residues are normal or not. So the Jack-Barra test is just another perspective of that. By right, you want both p-values to be small so that they are telling us or the other way around, because the hypothesis is that the residues are normally distributed, right? So for normality, the null hypothesis assumption is that they are normally distributed unless data tells me otherwise, right? The errors generated are so huge that it's deviating from normal, right? So by right, you want both to be failing to reject the null hypothesis. So p-value should be large. So we do have that. In this case, nan not a value because we have too few sample sizes. 5. Remember, it's meant for illustration only, not real values. So when you get nan, that means hopeless, gives up, right? So unable to. Of course, if you can, you try to increase sample size. But as we have said many times, even if you have money, doesn't mean that the samples will occur, right? Because they are rare, they are very hard to find, they are impossible or very, very occurring rarely or occurring only when many differently controlled measures and variables happen to be aligned, then you can have your sample, so then it's tough, right? Okay, and lastly, you have the Durbin-Watson test statistic. This number is a sort of a measure of the residual. So everything below here, look at the residuals. The residuals, if they are having any autocorrelation. So this number measures the autocorrelation. So if it is around 2, around 2, like 2-ish, like 1.5, 2.5, something like that, 2-ish, then it's good. Then it's good. That means there's no autocorrelation. The residues don't have autocorrelation. But if it is closer to 0, then it is positive autocorrelation. Or near to 4, then it is negative autocorrelation. So 2 is in the middle, right? 0 means positive autocorrelation. That when a value for a residue is large, it implies that the next residue is larger. Then the next residue is even larger. There's positive reinforcement, correlation, right? So I can tell. That means the correlation exists, that when your Durbin-Watson is close to 0, there is strong positive correlation. I know this current value of residue, it predicts or foretells or strongly correlates with the future residue in a positive way. So that means the next residue will tend to be larger and larger and larger, leading to non-homoscedastic kind of situation, which means problematic, right? We will break the homoscedasticity assumption. Similarly, if it is close to 4 or exactly 4, that means it won't be larger than 4 by the way the formula is constructed. So 3.95, 4 means negative, very strong negative correlation. I know this residue is 1. The next one confirmed is going to be smaller. Next one is confirmed going to be even smaller. 0.9, 0.8, 0.7, 0.6. If it is mildly larger than 2, right, that means it's mildly negatively correlated. It means I know this residue is 1. Next one, more high chance it will be lower, but it's 1.1. Next one, 0.9. Right? Next one, maybe 0.95, then 0.8. So it's like go up a little bit, but go down more, go up, down, but mostly down. Like stock price, right? Mostly down, sometimes up, but not much, not enough to salvage the trend of going downwards. So the closer to 2, the more diffuse the errors, the more unpredictable in some sense the errors, and so they don't correlate with all other residues, then that's good, right? So of course, the Durbin-Watson is just presented to us to try to let us have a quick glance, and of course, since it's presented, you want to have a look, right? So basically, that's it. And the table here is really, at one glance, able to tell us a lot of stuff, right? Including a quick check on the assumptions as to whether we are in serious problem, right? In serious challenge to the assumptions, then we better be very careful. Like I said, we don't immediately reject our data and then, kind of delete the whole project, but we just want to know where we stand. Like I said, there are many situations where after spending all the money, budget, and time to gather the data, it amounts to nothing from the analysis, right? You don't throw away everything. You want to salvage, maybe, regroup, take a subset of the data or whatever it is, right? Or be qualified in your announcement or publication or narration of your conclusion, right? And all these are things that you can do only after such a detailed human analysis of the results, right? So getting these numbers these days, so rich and output, right, from the little bit of random data that we fed in, getting such rich analysis coming out with just one function call in Python, roughly one function call in Python, is a luxury as far as data analytics is concerned, right? So it remains in you, right, or us, trying to read this output thoroughly and intelligently. And you can only do that wisely when you have the help of the theoretical foundation. So I hope today's video has given you all the necessary ingredients in trying to know how to wield this tool, this multiple linear regression tool, a lot wiser, a lot more powerfully, right, than before. Thank you very much for your attention and see you in the next video.